Hello everyone, good evening. Dear students, join immediately. Once all are joined, we can start our session. I think few are joined. Yes. Hi, hello everyone. Join immediately. Once all are joined, we can start our session. Yes, people are joining. Yes, hello everyone. Yeah, hello. Yeah. Yes. Join immediately. We can start our session. Yes, people are joining. Yes, good evening all. Good evening everyone. Yes, Hafiz, Dhruvil, Siddharth, good evening. Good evening all. Yes, Pavitra, good evening. Yes, Hiba, hi, good evening. Yes. Yeah, I think people are joining. And my dear students, as you are a day away from your board exam, hope you all are feeling confident and are in the final stages of your preparations. Hope you have revised organic and physical chemistry chapters which we have done in the last 2 days. Now I will brief on inorganic chemistry, which includes 2 major chapters, that is coordination compounds and DNF block elements. We have one more chapter, a minor chapter includes in this category, that is biomolecules. See, we are going to discuss almost all repeated questions of board paper. From board paper, so many repeated questions are there from this chapter. That all we are going to discuss. Okay, that way we can cover almost all topics of these chapters. So unlike MCQs, today we are going to discuss the descriptive questions. So note it down, almost all important points and the shortcuts which will help you in the upcoming exam. So I think almost all are joined now. Once again, welcome you all for today's session. So today we are going to discuss inorganic chemistry. So we will start with coordination compounds. You know that one. So many topics are there which are very important in coordination compounds. So for these topics, I selected very repeated questions from board papers. By that way, we can cover almost all topics. Yes. Now we will start our session. Be active, listen, note it down everything, and we can go for the session. See, for these three chapters, the weightage is almost same. We have coordination compounds, the DNF block elements, and biomolecules. So now we will start with coordination compounds. See, topic-wise questions I selected. So we will go for IUPAC naming. You know that two possibility for this topic is, they may give the formula of a compound, a coordination compound, and will ask you to write the name. 3 different compounds are here. We will write the name first. The another type question, as you know, they may give the name of the coordination compound and you have to write the formula. So one type question might be this one. So we will do the naming first. Okay, so we can start. Write down the IUPAC name for each of the following complexes. No, it is easy question. So we have the complex CONH3 5 times Cl2. So you know the oxidation number of the central metal atom we need to find out, that is cobalt. You can write directly or you can take it as, here the cobalt if you are taking it as X, okay, X plus NH3 anyway neutral ligand, so we will be getting 0, okay, plus we have 1 chlorine inside and 1 chlorine outside. For oxidation number we need to consider all ligands which are linked by secondary valency and primary valence. So we have to consider both chlorine. So I am taking directly 3 into minus 1 is equal to 0. Then we can write X is equal to plus 3. Anyway, oxidation state of cobalt is 3. So I will write the name below. Okay, the name for the first one, A. We have amine, NH3 ligand. Yes. Yeah, people are writing correct. So amine and chlorine. Okay, chlorido or chloro you can use. So I will write the name directly, pentaamine. Okay, pentaamine. After that, you know that one, monochloro, or you can write chloro or chlorido. It's same only. Okay, chlorido or chloro. It's same. Pentaamine, chlorido or chloro you can write. Then after that we have to write cobalt. Okay, within bracket we have to write the oxidation state, that is 3. Then outside the coordination sphere we have chlorine, so we have to write what? Chloride. It's easy one. Pentaamine chloro or chloro, pentaamine chlorido, cobalt 3 chloride. Yes, correct. Now we will go for the second one. It's a different one, so that's why I selected the other one. Okay, so here you know that one, it is an anionic complex. How do you know that it's an anionic complex? An anionic complex means if any ion, you know, counter ion we learned, if they're on the left hand side, then the sphere will get a negative charge. So while writing the name of a anionic complex, you know that one, the central metal atom name should be ending as what? 8. So I'll write the name here. Anyway, the oxidation state you can find out. Potassium 3 is there, we will take it as plus 3. 1 potassium is plus 1. Then iron you can take it as X plus, you know that one, 4Cn, so 6 into minus 1 is equal to 0. So anyway, X is equal to plus 3. I'll write directly. So after that, you can write the name here. See, B, potassium is there, that we have to write first. So potassium. Okay. After that, hexacyano. Cyano because of Cn. Hexacyano. Iron is the central metal atom, but because of a anionic complex, we have to write ferrate. Isn't it? Ferrate. So potassium hexacyanoferrate. Then within bracket, what is the oxidation state? 3. Potassium hexacyanoferrate 3. That is the name of the second one. Then the third one, the name. Here also you can find out the oxidation state. Here, chromium is the central metal atom and it's a different one. That's why I selected this one, because here it's a both cationic and anionic part are complex, because some complex compound may contain simple cation and complex anion, or simple anion and complex cation, like that. But here both cation and anion are complex. So how do you name this one? Here you know that one, Cr and Co both are central metal atoms. So I can take it, though it is a different metal, we will take it as 2x. Okay, X for this one and X for this one. Anyway, ammonia no need to consider because it's a neutral ligand. We can take it as 0 plus Cn is 6 into minus 1 is equal to 0. Anyway, 2x is equal to 6. We will be getting X value equal to 3. So for both the metal, we will give the 3. But in some cases, it will be, yes, cyanido can also be used, no issue. Cyano or cyanido you can write, no issue, correct. Yeah. So here we can write the name first. This is the cationic part and this is the anionic part. Keep in mind. So the name will be hexaamine. Okay, for the first one, hexaamine chromium. Hexaamine chromium. Then within the bracket of that, we will write the oxidation state of the first central metal atom, that is Cr. After that, we can continue. Ligand should be named first. We have hexacyano. Okay, or cyanido is fine. Hexacyano. Here we need to write cobaltate, not cobalt, cobaltate. Okay, don't forget, because the right hand side part is an anionic complex. Yes, cobaltate. So hexaamine chromium third, hexacyano cobaltate again third. Okay. So this is the way you have to name the complex compound. One question you can expect, okay, for IUPAC naming. But sometimes they may give the name and will ask you to write the formula. So I'll write the formula of these two complex. Okay, so here, yes, two names are there. Pentaamine, nitrito O. You know that one? Nitrito is an ambidentate ligand. Ambidentate means you know that one, right? Either with nitrogen or with oxygen, it can be linked or joined to the central metal atom. So here it is joined with oxygen. So I'll write the formula of here. After that, I'll tell you how the formula can be predicted easily. So pentaamine nitrito cobalt. So cobalt is the central metal atom. So I'll write CO. Then pentaamine means we can write NH3 5 times. Okay. Then after that, nitrito. Mononitrito means one nitrito is there. So that you have to write it as ONO, because O nitrito they are saying. O nitrito because it is linked with oxygen. Otherwise, you can write NO2 if they are giving nitrito N. This is nitrito O. After that, chloride. Chloride means we can just put Cl, but the formula is not over. Means the formula we have to adjust the number of Cl. How we will be adjusting? Either of the way you can do. The one method is cobalt should get the oxidation state as what? 3. Right now you know that one. Here NO is what? NO or NO2 is charge is what? -1. Chlorine one more is -1, which means you know that one, it will be -2. -2 become +2. Not +2. One more negative charge is required. One more negative charge is required means you have to put Cl2. Okay, because inside the coordination sphere we cannot make any change in the number of ligand because it is fixed. Secondary valency 5 plus 1 6. So we can add one more chlorine, then you know that one -2 -1 -3 become +3. Now the formula is correct. Yes, CuNO3 5 times NO. Now potassium tetracyano. Okay, so from board paper. So potassium tetracyano. So potassium tetracyano means you know that one, wherever they are saying potassium. So I'll write over here. Yes, potassium tetracyano. So you can write K left side. Okay, so after that we can start coordination sphere of the square bracket. Then tetracyanonickelate. Nickelate means Ni. Tetracyano means you know that one, Cn 4 times. Coordination sphere. But you know that one, the number of potassium atom you need to adjust. How? Here the nickelate oxidation state is 2. Nickelate oxidation state is 2 means you know that one, Cn is 4 over here. 1 Cn means you know that one, it is -1. So 4 Cn means what? -4. -4 and 2 should be there. Then only X will get as +2. So you have to put what? K as 2. Which means potassium is 2 and Cn is -4. So +2 and -4 become -2. -2 become +2 when you are taking the oxide state of nickel. So this is the way we will write directly or easily. So for exact formula is K2NiCN 4 times. Yes, correct. So now you understood, if they are giving the formula of the complex compound or the name, how to write the name. If it is formula is there, or if the name is there means how to write the formula. Okay. So this is the one expected part. Okay, now we can go for the second. See, another topic, you know that one, the very important one, VBT. Valence bond theory is used to predict, you know, hybridization and magnetic property. I just gave us VBT, you know that one, what is VBT? VBT method, VBT theory is used to explain hybridization and magnetic property of complex compound. So you see, we have 3 compounds, okay, to explain hybridization in the following complexes. Even we can say the magnetic property, you know, right, how to predict the magnetic property if you have the hybridization or if you are able to find out. Yes, yeah, we can go. See, the first complex I will write over here, Mn, okay, Cn 6 times, manganese Cn 6 times, coordination sphere 4-. What we need to do? We need to find out the oxidation state of Mn. I'll write directly Cn is Cn 6. So -6 is there. 1 Cn is -1. -6 when comes to right hand side, +6. +6 and -4 means +2. So in this complex, Mn is what? Oxidation state +2. Mn +2 means I'll write the oxidation electronic configuration, outer electronic configuration directly. We will get 3d5 4s0. Because Mn normally is what? 3d5 4s2. Mn 2 plus means, or +2 means, it is 3d5. 3d5 means you know that one. I'll draw the d orbital like 1 2 3 4 5. So we need to arrange 5 d electrons and s is anyway vacant. So this is 4s 3d. Why I drew this one? Because we need to find out the oxidation, hybridization over here. Here the coordination number is what? Coordination number is 6. 6 means 6 orbital we have to use. So I will do one thing. We can give the electron. While giving the electron, keep in mind Cn. What is Cn? Cn is a strong field ligand. SFL we can say. Cn is a strong field ligand. You know that one, strong field ligand means it goes pairing up of electron. So actually we have 5 electrons over here. So 1 2 3 4 5. But because of Cn, pairing up of electron takes place. How the pairing up? This will pair up over here. Okay, so this will pair up over here like this to them. This electron will pair up over here and this electron will pair up over here. So now we have, this one is empty. So here one pair of electron can be donated by Cn. Here it can be donated and S can be donated. After that what will come? P will come. You know that one. Here P will come. Not over, because we have 2d over here. So the hybridization is d2sp3. Why we select? We need 4 empty orbital because 4 ligands are there. So we can write directly, okay, d2sp3. Okay, hybridization. Take the second one. Second one, chromium. Keep in mind chromium and ammonia. You know the exception, right? Whenever NH3 is linked with chromium and one more is there, you know, which is the another metal exception. Yes, copper. Good. So whenever NH3 interact with chromium and copper, there is an exception. What is the exception? NH3 is normally a strong field ligand. SFL we can say strong field ligand. But with Cr and copper, chromium and copper, NH3 will act as a weak field ligand. So we have the complex Cr NH3 6 times. Coordination sphere 3 plus. I will write the oxidation state directly over here. Here the Cr oxidation state is what? 3 plus. Okay, because here it is 0. Cr 3 plus means I can write 3D. Okay, 3D3. Sorry, chromium means what? 3D5 4s 1. So 2 electron is going means you will be getting. Okay, normal chromium normally will be what? 3D5 4s1. So you need to remove 3 electron. Okay, 3 electron means 2 from this one and 1 from this one. So you will be getting 3D3 4s0. That 3D3 and 4s0 we can draw over here just for understanding that exception. So we have 3 electron. Okay, 3 electron 1, 2, 3. Here NH3 though it is a strong field ligand, here pairing up cannot be followed, or it cannot do the pairing up because we don't have any hybridization other than or more than D2. So now already here 2 orbitals are vacant. So we will take this one and this one. Now we have D2. S anyway we can take because S is empty. This will we can take, and we can take again P. So these all P will be taking. Again, what is the hybridization? D2sp3. So we got the hybridization of first one as D2sp3 and second one as what? D2sp3. Here anyway pairing up will not take place. What about the cobalt? Cobalt, let us see, CONH3. Okay, 6 times, coordination sphere 3 plus. Here also I can write the oxidation state of cobalt. Here also I can write the oxidation state of cobalt as what? Cobalt is 3 plus. Okay, so cobalt 3 plus means because ammonia is 0. So I can write 3D6 4s0 because cobalt normally is what? 3D7 4s2. So 3 electron loss, then we will be getting 3D6 4s0. So 3D6 4s0 means we can draw the D subshell. Okay, and 4s is here. You know that when 6 electrons are there, that 6 electron with NH3, it's a cobalt. So here pairing up of electron definitely will take place. Normally will be 1, 2, 3, 4, 5. But these 2 electron I am taking. Okay, so 1, 2, 3, 4, 5 and 6 are there. Okay, so this electron I will take and will pair up over here. This electron I will take and will pair up over here. Here it undergoes pairing because here pairing up can take place and we will get an exact hybridization. Here it is impossible. So now we can use the 2 orbital over here and this one again. Here it is P. Okay, now the hybridization is what? Again D2sp3. D2sp3 hybridization. Yeah, here see, in case of chromium here you know that one Cr3 plus is the oxidation state and you have 3D3. Okay, so because chromium oxidation state is 3D, chromium oxidation state is 3 plus. So 3 plus means what will be getting? 3D3 4s0. See, normally chromium is what? 3D5 4s1 because you know that one half filled. We have chromium and copper, there is a change. So 3D5 and 4s1. So 3 electrons we remove, 2 from this one and 1 from this one. So we have 3D3, isn't it? So that 3 electrons we used over here. What I explained is NH3 normally is a strong field ligand. The effect of strong field ligand will not be here in this case, chromium. Yes, chromium, it will not be there because here if it is trying to pair up also no use. This electron if it pair up over here, we will get 3D orbital. We don't have any hybridization like D3. We have hybridization only like D2. Yes, we have hybridization only like D2sp3 because octahedral is the shape. See, octahedral is the shape. Coordination number 6 means what is the shape? Octahedral. Octahedral means either what will come? D2sp3. Okay, octahedral has either D2sp3 or sp3d2. This is the only will come. Okay, this is the way you have to find out. So keep in mind NH3 has, yes, NH3 has exception with the chromium as well as copper. That's all. So that's why I selected this one. Normal, this one is normal and this one is normal, but this one is an exception. With the copper also exception is there. Okay, we will go to the next. This question is again based on VBT. See, out of COCl6 3 minus and COEN thrice 3 plus, which complex is paramagnetic and diamagnetic? This one you can do. Yeah. Yes, this is an easy one anyway. So I will write the compound separately. COCl6, coordination sphere 3 minus. Here I will write the other one. COEN thrice, coordination sphere 3 plus. Now listen. Here we can find out the hybridization if you want, then we will get whether it is paramagnetic or diamagnetic. Here I am going to write the oxidation state directly. Yes, so here you know that one, chlorine is minus 6. Minus 6 when comes to right hand side, plus 6. Plus 6 and minus 3 means cobalt is what? Plus 3 oxide state. Okay, plus 3. Plus 3 means we wrote just before, it is 3d640. 3d640. 3d640 means you know that one, 3d has, okay, orbital, and this is 4s. So 6 electrons are there. Cl is what? It's a weak field ligand. Chlorine is a weak field ligand. So for weak field ligand, how do you distribute the electron? Here it is 1, 2, 3, 4, 5, 6. Anyway, pairing up will not be there. Pairing up will not be there means we will be using S. This is the 4s. This is the 3d, and again we need to use this P. Then it will not be over. Again we will be taking D, outer D. This is which D? 4D. You are getting idea? So we will be taking 2D. So what is the hybridization over here? Here the hybridization is sp3d2. Why I wrote this one? Because they are asking whether it is outer or inner orbital complex. By writing this electronic configuration by d electron, we came to know that this is what? Magnetic, paramagnetic. So which one is paramagnetic? COCl6 3 minus is a paramagnetic one. Yes, very good. This is outer orbital complex. How do you identify it is outer orbital? Outer orbital means if outer d subshell is used for hybridization, it's called outer orbital complexes. Inner d is using, in the previous case we got d to sp3. Coordination number 6 means either d to sp3 or sp3 d2 only we will get. Yes, first one is outer D. Outer D is making use for hybridization, that's why. Then we can go for the next. Here also you know that one, En is a neutral ligand. What is the oxidation state of cobalt? Again 3 plus. No need to write actually, because you know that one, the same will come. So I will do one thing, 3d640 only will come. 3d640. So here what will happen? Pairing up of electron occurs, because yes, chelation, and En is a didentate ligand. Obviously it's a chelate complex. En comes under what category? It's a strong field ligand. Okay, yes, En is a strong field ligand. So what will happen? I will write the D over here. Okay, this is 3D and this is the 4s. So how many electrons actually we have? 6 electrons are there. So 1, 2, 3, 4, 5 and 6 are here, and I will take this electron. Okay, no need to waste the time by erasing the electron, that's why I am writing this way. 1, 2, 3, 4, 5, 6 I gave. I'll take this electron and will pair up over here. I'll take this electron and will pair up over here. Hope you got. Now we have 2 d orbitals vacant which can be used for hybridization. So 2d I used, 1s I used, and 3p we can be making use for hybridization. This is 3d, 4s and 4p. Only inner D subshell is used for hybridization. So what is hybridization? D to sp3. So D to sp3 means inner D orbital or inner D subshells are used, means it is an inner orbital complex. Inner orbital complex. Here none of the electrons are unpaired. All electrons are paired. All electrons are paired means you know that one, it is diamagnetic. So diamagnetic. So this type of one question. See how En is a strong ligand. So we are in the edge of exam. Now you are asking what is how En is a strong field ligand. Anyway, see we have spectrochemical series as a part of crystal field theory. You know that one, VBT has so many limitations. One important limitation is what? One important limitation of VBT is that it could not categorize which all ligands are strong, which all ligands are weak. But whenever complex forms, we know that one, these are strong, these are weak, because pairing takes place in some case, pairing will not take place in some case. So that is the one limitation of VBT. To overcome limitations of VBT, we have a theory called CFT, crystal field theory. They gave a list of ligands, you know that one we have, right? I minus, F minus, Cl minus, Br minus, I minus, after that OH minus, after that C2O2 minus, after that H comes, or H2O comes, after that NH3 comes, after that Cn comes, after that ethylene diamine, that means En comes, after that CO is the strongest ligand. So we have that series. Based on that one, you know that one, this is a, En is a strong field ligand, pairing up will take place. So that order you need to keep in mind, or else you have to keep in mind which all are strong at least. Remaining all are weak, that you can keep in mind. So which all are strong? NH3 is strong, but I gave an idea, two cases exceptions are there. Which all two cases? NH3 with the CR, NH3 with the CU. Exception is there. Otherwise, remaining all NH3 is strong. After that, which will come? After NH3, you know that one, ethylene diamine is there. After that, Cn is there. After that, NO2 is there. After that, Cu. These all are strong field ligand. At least you have to keep in mind these all are strong field ligand. SFL normally. This one has an exception that I gave you. Fine. Okay, Aravind. So based on that one, this type of question you can expect. So we explained everything. Which is paramagnetic? This one. Which is diamagnetic? We got. Which is more stable and less stable. That we can explain based on which one? En. Yes. ED, TA or CO. That ED, TA and all, normally the complex will not be forming, or we will not get any question with ED, TA. You know that one, it's a polydentate ligand. CO, that for entrance and all, we will learn that one. Here you keep in mind only CO. CO is the strongest ligand for board exam. Okay, CO. Carbonyl is the strongest ligand. Fine. So which is more stable? More stable is which one? This one. More stable. Why? Because when there is a didentate or a polydentate ligand, it forms a chelate complex. Chelate complex means, you know that one, di or polydentate ligand when attached to central metal atom, it forms a ring-like structure, a cage-like structure. That chelate effect, you know that one, chelate effect. So chelate effect gives extra stability. Because of that chelate effect or chelate effect, this is more stable. Comparatively, this is more stable and this is less stable. So we explained everything. This type of one question you can expect. So now this part is over. I think there is no chance of confusion. Everything is fine. Okay. Now we will go for the fourth question. So we need to cover almost all topic. Okay. Then this is the final stage. So almost all topic we need to go through the questions. Then and only you will get the ideas, because these all are the type of question you can expect. See, third one is what? Crystal field theory. That's what I told, CFTK. To overcome the limitation of VBT, we have CFT, though it has limitation. I think question will come. Give the electronic configuration of the following complexes. Here also I kept one exceptional thing. This is the question from board paper, previous board paper. Give the electronic configuration of the following complexes on the basis of crystal field splitting theory. I'll give a small idea about what is crystal field splitting. Naval. Inner and outer orbital. That's what I explained. No, there is a doubt. Wait for a few seconds. Inner means what? Inner orbital complex means what? Quite easy. See, inner D. See, we have two types of d orbital, right? 3D and 4D. Here 3D, none of the orbitals participated. Only which D is participated? Outer D. 4D. That's why it is outer. In this case, the outer D is not participated. Only which one is participated? Inner D. That is why these type of complexes, inner orbital complexes, will be low spin. Low spin means all are paired, spin of complex will be less. Here only outer D is used, which means electrons are unpaired, then more spin will be there. You got? Okay. So now we will go for the CFT. Crystal field theory, you know that one. When ligands are approaching central metal atom, it creates an electric field. In that electric field, the central metal atom, okay, the degenerated d orbital of the central metal atom splits into two sets. What are the two sets? T2G and EG. For, you know that one, T2G and EG. So T2G consists of three orbitals. The diagram and all I'm not drawing, you know that one. And here it will be T2G and EG. It splits two. So the degenerated d orbital, 5d orbital, splits into two. Okay, so it splits into two, that is T2G and EG. This is called crystal field splitting. Based on this one, they could explain why complex compound exhibit color, that all they could explain. So now here they are asking, in these complexes, what is the T2G electronic configuration and EG electronic configuration? This type of one question you can expect. So crystal field splitting theory, okay, I'm not going to explain in detail. This is not the right time for that. So this is just, we will do the question based on that concept, then you will get the idea. Otherwise, the one concept, if I'm teaching the last moment, we won't be able to touch any other topic. So almost all topic we can touch with this. So this is the way crystal field splitting happens. Now listen. So here we will take the first complex COF6 3-. This is also an easy one. You just listen this one, how to write. Then you can do the next question yourself. Yeah, let's see. Yes, Dhruvil. First 3 is T2G. Yeah, that is. So here, first you find out the oxidation state of cobalt. What is F6? F is -1. -1 into 6, -6 when comes to right hand side plus 6. So cobalt is 3+. That you understood, right? Oxidation state of cobalt is 3+. Then what is the electronic configuration comes? Electronic configuration comes for cobalt 3+ is 3d640. In many cases they will give cobalt, so you can easily remember 3d6, because normal cobalt is 3d740, that you remember. So CO3+ means 3d640. So 3d640, and what is the ligand over here? Fluorine. Fluorine is a strong or weak? I gave a list of strong. Other than that, all are weak. So this is what? WFL. What is WFL? Weak field ligand. Weak field ligand will not pair up electron, so will not cause pairing up of electron. Will not cause pairing up of electron means how will you distribute electron? 1, 2, 3, 4, 5, 6. There is no pairing up. 1, 2, 3, 4, 5, 6. So now how many you got in this one? You got 4, right? So I will write T2G4. Okay, and EG how many? 2. So this 6 I am distributing 1, 2, 3, 4, 5, 6. So here total I got 4, here 2. Fine. This is the configuration we need to write. So T2G4, EG2. Yes, good. People are sending. Yes, yeah. Me now. Yes, Hiba. Yeah, correct. Now we will take the second one. Second one is what? Now I think you got the idea, right? FeCN 6 times. Coordination sphere 4-. Here I will write the oxidation state of the central metal atom, that is Fe. Fe -6 and -6 when come to right hand side plus 6 and -4 is what? +2. Okay, we can write directly. So Fe2+ means what is the electronic configuration? We will be getting 3d640, because normally Fe is what? 3d640, only 2 electron lost. So we will write 3d640. But keep in mind, Cn is what I gave in the list. Cn is a SFL. What is SFL? Strong field ligand. That only strong field ligand you keep in mind, I gave in the previous case. That's what I told you. Important thing, you note it down. Okay, we don't have again time to learn all these these things, you note it down. 3d6 and 40. So, but here you know that one Cn is a strong. Being a strong, it goes forward pairing up of electron. So whenever pairing up occurs, you know that one electron 1, 2, 3, 4, 5, 6. Okay, and these two will be pairing up over here. So 1, 2, 3, 4, 5, 6 we will arrange, and these two, this will pair over here and this will pair over here. Then what we will get? We will be getting the electronic configuration T2G 6 and EG will be what? 0. Yes, T2G 6, EG 0. Correct. Good. Then take the third one. Third one, can you see any exception over there? The third one, if you got the idea about the exception of nickel. Yeah. Yes, Hiba. So CuNH3 is 6 times coordination. Sorry. CuNH3 6 times coordination sphere what? 2+. Here you know that one, and Cu is in what oxidation state? 2+. Directly we can write Cu2+ means what is the electronic configuration comes? 3d940. Keep in mind, what is that? 3d940. Why 3d940? NH3 here will act as a weak field ligand. Yes, Allah Muhammad. Yeah, that's what I explained just before. Yes, good, well done. Because here you know that one, keep in mind, should not make mistake over here, because in copper 3d9 means you know that one, if you want you can write normally this one first. If you have confusion 1 2 3 4 5, you know that one 9 means 1 2 3 4 5 6 7 8 9. So here anyway there is no chance of pairing up of electron, because 9 means where we will pair up? There is no pairing up of electron. Pairing, if it is trying to pair up also, there is no such hybridization, right? There is no hybridization, like, because here coordination number is what? 6. Coordination number 6 means either D2sp3 or what? sp3d2 is there. There is no hybridization like dsp3d. No. Because here if we are getting one D also, there is no use. That is why pairing up will not take place. So how the electron will go? We can write like 1, 2, 3, 4, 5, 6, 7, 8, 9. So here anyway will be 6. So I will write T2G. Okay, 6. EG will be how many? 3. How many of you got the correct answer? Yes, well done. Half S. Yes, this is what I told you. So NS3, T2G6 and EG3. So in two cases, yes, so in these cases with the copper and chromium, that you keep in mind. So here anyway pairing up will not take place. With copper, NS3 is weak. So we got the electronic configuration T2G6, T2G6, EG3. Correct. Okay. Now crystal field theory, this based on the splitting up, one question you can expect. We will go to the next. Yeah, see, this is a theoretical question. Theoretical question, I told you, they are asking what is crystal field splitting energy. Crystal field splitting energy, I told you, this is crystal field splitting. What is crystal field splitting? The process of splitting up of degenerate d orbital. What do you mean by degenerate d orbital? D orbitals are having same energy before splitting. So the process of splitting up of degenerate d orbital into two sets, that is T2G and EG, is called crystal field splitting. Whenever crystal field splitting occurs, you know, there is a difference in energy that we usually represent as delta O for octahedral complexes. Tetrahedral if it is, we will write it as delta T. So what is delta O? That delta O is called the crystal field splitting energy in octahedral complexes. So they are asking about that delta O, or generally crystal field splitting energy. So the difference in energy between T2G and EG in crystal field splitting is called crystal field splitting energy. Quite simple. The difference in energy between T2G and EG in crystal field splitting. Yes, the difference in energy between T2G and EG in crystal field splitting is called crystal field splitting energy. So first one is over. On the basis of crystal field theory, write the electronic configuration of D6. It's another type. Previous question is another type because they gave the complex and they are asking to write T2G and EG. Here they are giving the two condition. You know that one, on the basis of CFT, write electronic configuration of D6 in terms of T2G and EG. In terms of what? T2G and EG. In octahedral complexes, you know that one, in octahedral complexes, the condition first one is what? Delta O, that is octahedral splitting, greater than what? P. What is P? Pairing energy. What is pairing energy? The energy required to pair up electron. Here they are saying the splitting energy, octahedral splitting energy is much more than that of pairing energy, which means what? Pairing occurs. So pairing energy is less, this is more, means enough energy is there to pair up electron. What is the configuration they are giving? 6, D6, right? So D6, how do you arrange over here? See, T2G, okay? T2G6, then EG will be what? 0, because pairing up will take place. In the previous case we drew, you know, down it is 3 orbital 2. So all the 6 will be pairing up in the down because octahedral splitting energy is much more than pairing. So this is the energy required for pairing, but the octahedral splitting energy is much more than that, means enough energy is there, so pair up. So what about the second one? Second one is the condition is opposite. Delta O less than P means pairing energy is much more than the energy produced by octahedral splitting. So by octahedral splitting, yes, there is a, here no need to consider any SFL or WFL. Here they are giving the condition. So condition means what? Pairing energy is more over here. Pairing energy is more means more energy is required for pairing up. So pairing up will not take place. Pairing up will not take place means what? Here 6, how will you arrange? So 1, 2, 3, 4, 5, 6. So T2G will be what? 4. EG will be how many? 2. Pairing process you understood, okay? I'm not going to draw again, it will be a waste of time. So 1, 2, 3, 4, 5, 6, which means here it is 4, here it is 2. That is the way we got this one, T2G4, EG2. Yes, P plus and D, correct, T2G4 is. This type of one question you can expect. Yes, one more sub question is there. Write two limitations of crystal field theory. See, what are the limitations of crystal field theory? That also they asked in board paper. One important definition once again. Yes, definition of, I think this one, right? Crystal field splitting energy. It's simple. The difference in energy between T2G and EG in this process is called what? Crystal field splitting. After or due to the crystal field splitting, we are getting T2G and EG. Orbitals are separated, 3 over here and 2 over here. That definitely will be energy difference. No, this is the average energy. The energy less than that, this is the energy greater than that. So that much all deep we cannot go. That's why I'm just brushing up the concept and we will go for the question. So the difference in energy between T2G and EG is called crystal field splitting energy. So write the two limitations of crystal field splitting theory or crystal field theory. What is that? The first is, as you asked, according to crystal field theory, they are saying that negatively charged ligands are considered as point charges. Means a ligand having a negative charge means it can be considered as one negative charge. So as I explained, when these negatively charged ligands approaches central metal atom, it creates an electric field. So if negatively charged ligands are approaching, it creates a very strong electric field. Then the crystal field splitting should be more. Okay, unlike neutral ligands. Neutral ligands are when approaching, you know that one, it is neutral in charge, or we will call it as point charges. That one cannot create that much splitting. That is the logical thing according to this theory. But the order of the ligand is not followed this one. Okay, so what is the first limitation? Negatively charged ligands are expected to cause more splitting than neutral ligand, but the order is different, because you know that one, which is the strongest ligand we consider Cu, but H2O is neutral. Okay, H2O, you can take OH minus. OH minus is a negatively charged ligand. This is weak, but this is the strongest. So that is a one limitation. Another limitation, they are considering only d orbital for crystal field splitting energy and ignores s and p orbital. Even p bonding and all can occur, but they ignores s and p orbital. Two limitation if they are asking, one you write, negative ligands are expected to cause more splitting, but order is not followed. Order is not followed means in the crystal field spectrochemical series, neutral ligand cause more splitting. That is actually the practical fact. Second one, only d orbitals are considered for splitting, not s and p, you can say. That is the second limitation. Enough. Faris, question is important means, see, for board exam we cannot say that this will not come, that will not come. No. These are from previous board question paper. Limitation of crystal field theory. Nothing is deleted means anything they can ask. Okay. So these are from previous board. This is very important. Which one? The limitation. Not the limitation. Limitation they asked in so many board papers. You can check the previous paper. This is very important. This delta O type. Delta N. Yes. We will go to next. Question number 6. CO2 plus is easily oxidized. These are again from board paper. CO2 plus is easily oxidized to CO3 plus in presence of a strong field ligand. Give reason. Okay, CO2 plus is easily oxidized to CO3 plus in presence of a strong field ligand. I told you CO3 plus means what? CO3 plus means electronic configuration is 3d6 4s0. What about SFL, strong field ligand? Strong field ligand will pair up the electron. So pair up the electron means, you know that one, we have T2G. Okay, here this is T2G and we have EG, 2 orbit. Okay, so when 6 electrons are there and it's a strong field ligand, what happened to the electron? Electron will pair up in here itself, 1, 2, 3, 4, 5, 6, and these two will be pairing up. So we will be getting all are paired. Then what we got? We got completely filled. Okay, completely filled what? T2G. Anyway, completely filled T2G has stability. So what do you need to write? Yeah. Don't send the messages in Hindi and all, okay, send in English. So CO3 plus, it is 3d6 4s0. So 3d6 4s0, that means Electronic configuration is 3d640 SFL. Strong field ligand means the pair up of electron takes place. Then completely filled T2G will come. Completely filled T2G gives extra stability. So you have to say that a strong field ligand CO3 plus has 3d640 electronic configuration, and a strong field ligand can pair up the electron and it will give completely filled T2G. So completely filled T2G is there in your answer, they will give you mark. So the first one is over. Go for the second. On the basis of crystal field theory, write the electronic configuration of D4. These are the questions from different board papers. Again they are asking D4. D4 and the condition is what? Delta O less than P. You do yourself. Yes, Alan Joseph Kurian. Yes. Yes. See, delta O less than P. So delta O less than P means, you know that one here, pairing energy is much more, means pairing up will not take place. We have T2G. Okay. You know that one, T2G, here will be 4 means 1, 2, 3 and 1, 4 over here. So T2G 3, EG will be what? 1. Okay. Because pairing energy is much more than the delta O. Delta O is the octahedral splitting energy, so much more. So we will be getting no pairing. Yes, yes, here pairing will not take place. Yes, yes, Fijas, yes, pairing up will not take place. So pairing up will not take place means we know that one, here it will be only we have 4, so 1, 2, 3, 4, so EG will be 1. Okay, only D4 is there, that's why we are. Now we will go for the next question. So next question is, see, next question is NiH2O 6 times 2 plus is a green colored compound becomes violet. It's another type question. So becomes violet when ethane 1,2-diamine. It is nothing but what is ethane 1,2-diamine? That is ethylene diamine, En. So when En ligand is added to this complex, they are saying the color will change from green to what? Violet. This is from previous board paper. I'll give you an idea what is the logic behind this question. You know that one, the crystal field splitting depends on the strength of the ligand. If a strong ligand approaches, crystal field splitting will be large. Why? Because for crystal field splitting, the complex should absorb light of more energy. Light of more energy means, you know that one, based on wavelength we can say. So light of more energy is required, or it will absorb light of more energy for crystal field splitting if strong ligands are approaching. What if weak are approaching? If a weak field ligand is approaching, crystal field splitting will occur. Then for crystal field splitting, the complex will absorb light of lesser energy. So here that means, you know that what energy it is absorbing, it emits the energy, and that decides the complementary color or the color of the complex. So based on what energy light it is absorbing, it will give, yes, more energy. Yes, light of more energy is absorbing means a particular color. Light of lesser energy is absorbing means a different color will come. That only, no need to memorize the color or what color will come, that we can't even predict. So the logic of the question is, here they are saying, I will give the idea, NiH2O 6 times, coordination sphere what? 2 plus. This when treated with En, you know one, 3 En we will be adding because it's a didentate ligand. When this ligand is added to this one, it will substitute H2O. It will substitute H2O means the complex will be forming like this one, NiEn thrice. Coordination sphere, what will come? 2 plus. Because it's a neutral ligand. Here 3 because En is itself is a didentate, 3 into 2, 6. Anyway, coordination number, everything is same only. But here En is what? Strong field ligand. This is what? A weak field ligand. I told you H2O is a weak field ligand. So here light of lesser energy will be absorbed. That is why the color is what? Green. So light of lesser energy is absorbed for excitation of electron. You know that one, light of lesser energy is absorbed and undergo DD transition. DD transition is nothing but T2G to EG. Here it is, what is the color? Color is violet. Why it is violet? Because strong field ligand, which means light of more energy is absorbed, then the complementary color will come as violet. Okay, so here for DD transition, light of more energy is absorbed. That only you need to tell. So answer is, when En is substitute, okay, ethylene diamine is a strong field ligand which substitute the weak field ligand H2O. light of more energy should be absorbed for DD transition over. That is the right answer. An added strong field ligand, more energy light is gained. Yes, half is, that is the right answer. So it should be in complete sentence. When a strong field ligand substitute a weak field ligand, it absorbs light of more energy for DD transition. That's what the color is different. Explain the following. It's a related question. That's why I gave anhydrous CuSO4. It's related in the sense anhydrous CuSO4 means, you know that one, there is no ligand, because CuSO4 anhydrous means no ligand, because when water is added it acts as a ligand. No ligand means what? No DD transition. No DD transition. Non-DD transition means no color. White means colorless in chemistry. What about hydrated CuSO4? You know that one, hydrated CuSO4. Okay, hydrated. See, hydrated CuSO4 has a formula. You know the formula? It is CuSO4.5H2O. But according to complex compound, what we will write? CuH2O4 times, then SO4. Yeah. H2O4 times. Here, see, CuH2O4 times means this 4H2O will be directly attached over here. Then SO4. Okay, CuSO4. So here water acts as what? Ligand. There is a ligand added to this one. Okay, so when water is added to this one, okay, so water is when CuSO4, yeah, water is added when ligand. Ligand means what comes? DD transition comes. So DD transition. So you have to say that. Yes, colorless anhydrous called splitting up of d orbital is impossible. Yeah, that's what I explained. In other words, no ligand is present in anhydrous copper sulfate. There is no DD transition. DD transition means no color. Copper sulfate and hydrated copper sulfate consists of H2S ligand, which helps for DD transition. That is why we will get color. Next one is C. TiH2O 6 times Cl3 is violet color but becomes colorless on heating. Opposite of the first question. You have to say that TiH2O 6 times Cl3 is violet because H2O there is a ligand. So H2O ligand helps for DD transition, so it's violet color. When it becomes colorless, means it becomes colorless on heating. Heating, water molecule will be, yeah, water molecule will evaporates out. Therefore, there is no ligand. Okay, so water molecules separate out on heating. That is why there is no ligand. No ligand means no DD transition. Yes, H2O is liberated. Yeah, on heating, H2O escapes out. No ligand is present after all. Then no DD transition. That is the basic logic for these two questions. These type of questions are there for board. Yes, now we will go to question number 8. Question number 8, again the topic is isomerism. We have two more topics I think for this chapter, isomerism. So isomerism, you know that one, isomerism for complex compound and geometrical isomerism also, one question is there, we will discuss. See, what is the type of isomerism shown by this complex? So isomerism shown by this complex is what? Ionization isomerism. We learned 4 types of isomerism. First one is what? Ionization isomerism. What is ionization isomerism? Ionization isomerism is nothing but here the ions it produces. Sorry, the first one is not ionization. First one is linkage, right? Oh, yeah, I thought, yeah. First one is the linkage isomerism. Wait, here CuNO because ONO is given. ONO means it's an ambidentate ligand. Whenever ambidentate ligand comes, it's that isomerism is called what? It's linkage isomerism. So what do you mean by linkage? Linkage means a ligand can link. Okay, it can make a bond towards a central metal atom by using either of the donor atom. So here the linkage isomerism means I will write the next isomer of that, CONH3 5 times ONO, then coordination sphere Cl2. What is the linkage isomer of this one? That also they asked in board paper. The linkage isomer of this one is, so I will put an and symbol over here, CONH3 5 times, we will get NO2. Okay, because here it is attached with O, here it is attached with what? NO2. Okay, then Cl2 is same. So if it is linked with two different donor, yes, it's called linkage isomerism. Linkage, yeah, first one is linkage, fine, good. Second one is what? Second one, the type of isomerism, it's called hydrate isomerism or solvate. Both you can use the term hydrate isomerism. What is that? The number of water molecule inside the coordination sphere will be different. CrH2O 6 times, coordination sphere Cl3. And you can take one H2O molecule to the outside of the coordination sphere, then you will get Cr. You can write H2O 5 times, one Cl will come inside, then only the coordination number can maintain as the same. Then you will get Cl2 dot H2O, one water molecule will go out. Then you will get, yes, correct, it's called hydrate isomerism. Okay. Third one is ionization isomerism. So ionization isomerism means it produces different ions in aqueous solution. So what is the first one? First one is CONH3, means the isomer, first isomer is CONH3 5 times, SO4 is inside, then Cl is outside. This can produce this the same complex can be write in the form of NH3 5 times. Okay, so NH3 5 times you take Cl inside and SO4 outside, which means in the first case the sphere will have 1 plus and Cl will be, yeah, Cl minus will come. In the second complex, the 2 minus ion, SO4 2 minus ion will go, and the complex, the coordination sphere will get 2 plus. Both are having same formula but produce different ions in aqueous solution. Okay, the last one is what? Coordination isomerism, or you can say coordinate isomerism. What is coordinate isomerism? Isomerism which arises due to the exchange of ligands between the complex. So I will write here itself so we can save the time. Okay, I will write over here. So we have CONH3 6 times, Cr and Cn 6 times. How it will be exchanging? The Cr will be coming over here, so I can write Cr with NH3. So Cr NH3 6 times complex, and with the CO the Cn will come. CO, the CO is called Cn 6 times coordination sphere. These are isomers. Okay, so these are isomers. The only difference is that ligands are mutually exchanged. Yes, correct. Yeah, Faris. Okay. So 4 types of isomerism we learned. Any of the question they can ask. These are the previous board question. This is the way they ask. Sometimes they may ask like this one, or they may give the formula and will ask you what type of isomerism, or they will ask for example also. Okay. Now we will go for isomerism, another type. What type of isomerism is shown by COEN thrice 3 plus? You know that one geometrical and optical part is also there in this chapter. Geometrical isomerism and optical isomerism. Can you do the 9th one? Yes, you are getting idea, right, for this chapter? Whatever the question, this type of question, if you are getting day after tomorrow, you will score full mark. Hafiz, yes, optical isomerism, well done. So the complex given is COEN thrice, coordination sphere what? 3 plus. This is the complex. See, this complex only exhibit what? Optical isomerism. How do you predict that? Because this is the only one type of ligands. You know that one heterogeneous complexes and homogeneous are there. Okay, so heteroleptic and homoleptic. You know that one here it's only one type of ligand, means no geometrical, only what? Optical. How do you represent that? So type of isomerism shown by optical means you can write like this one CO. What is the coordination number over here? Coordination number is 6 because En is a identity. 2 into 3 is 6. So you can easily draw like this one: 1, 2, 3, 4, 5, 6. 6 coordination number. So how many En you have? 3. So I'll put one En over here. It's a identity, so I connected. I'll put one En over here, 2 connected. I'll put one En over here, and what is the oxygen state over here? 3, means the charge of sphere is 3 plus. So I drew this one. So now this is the ligand, means complex I represented. You can take the mirror image. Non-superimposable mirror image is there, means you will get the optical isomerism. So I'll write again same like CO: 1, 2, 3, 4, 5, 6. This En will come over here, and this En will go over here, and this En will go over here, and this 3 plus anyway we can write over here. If this is the D form, this is the L form. Yes. Not a cis and trans. Cis and trans cannot be exhibited because since all the ligands are same. Same type means no geometrical, only optical. Next one I will tell you. That's why I kept these 2 questions. So geometrical and optical. Cis is optically active. Here, next one. Yeah, correct. Good. Yeah, propti. Good. So the next is the complex is given as what? COEN twice. Check COEN twice Cl2. Coordination sphere has what charge? Charge is plus. So here you know that one, they are asking to write only the isomer which is optically active. So I'll give an idea how we will draw the geometrical first. This will exhibit geometrical because here the coordination number is 4, 2, 6 is there. Okay, total 6 because 4 plus 2, this is died and date. So 2 into 2, 4. So I'll give an easy method. I gave an easy method. This is the way. So you put CO first, then 1, 2, 3, 4, 5, 6. Easy. After that you can keep 2 EN. So I'll keep 1 EN over here and 1 EN over here. It's a died and date. So we will connect like this. 1 CL I'll keep, 1 CL I'll keep. Anyway, coordination sphere charge is plus. This is what CL, CL same side, EN, EN same side. This is cis isomer. They did not ask to write, okay, but I drew this one to understand. And you know that one, the trans we can draw. Trans, how do you draw? Again, put CO 1, 2, 3, 4, 5, 6. Trans means you can put 1 CL over here, 1 CL over here, 1 EN I will keep over here, 1 EN I will keep over here, EN, EN same side, CL, CL same side, plus char, this is trans. No need to draw this. I know the question they are not asking, but I drew this one to understand. Sometimes they may ask. But among this one, which is optically active, you know that one, if you are taking the mirror image of trans, you will get the same. If you are taking the mirror image of the trans, it will be same. So I will do one thing straight from this one. I will draw the mirror image over here. So the mirror image of this one will be what? CO 1, 2, 3, 4, 5, 6. Here the EN will come, right? And here the EN will come, and 1 CL will go, 1 CL. Anyway, this if you are keeping over here, it's not the, this one I'll put plus over here. So this is not the mirror image, means non-superimposable mirror image we are getting. So if you are taking this one as D, this one as L. So they are asking draw the geometrical isomer of EN twice which is optically active. So you need to draw only this. No need to draw this one. This one I drew just to understand. Yes, it's only. Yes, correct. Fijaz. MTK, Prapti, Alan, correct. So, yeah, we need to draw only this. Fine. Now we will go to question number 10. Hope you understood. This is the question based on Werner theory. One more topic, then this chapter will get over. Werner theory, you know, have you seen this question anywhere? Read the question first. Have you seen this question anywhere in the previous board, or have you practiced this? When a coordination compound having the formula COCl3.4NH3 is mixed with AgNO3, 1 mole of AgCl is precipitated per mole of compound. Write structural formula and name. Yes. Faris. Yes. How do you do this? This is based on Werner's theory. You know, Werner's theory says which all some ligands are attached with the secondary valency, some are attached with the primary valency. Secondary valency will be fixed, primary valency is temporary, ionizable. That theory is called what? Werner's theory. Yes. So this question is a repeated question. See, the formula they gave, COCl3.4NH3. In this one they are asking this compound when treated with AgNO3, excess of AgNO3 we will add. Okay, excess of AgNO3, you are getting 1 mole of AgCl, which means from this molecule only 1 Cl can come out. In the sense, this complex can produce only 1 Cl, means only 1 Cl is outside. Yes, half is. Well done. So that means you have to put only 1 Cl outside. Anyway, cobalt always will make a complex having coordination number 6, that you keep in mind. So I'll write CO, NH3, no change, NH3 4 times. Out of 3 Cl, 1 Cl is outside, that is this complex C. When AgNO3 excess is added, 1 AgCl is produced, means 1 Cl should be outside the coordination sphere. Because you know that one, then so I'll write 2 Cl inside, then 1 Cl outside. According to the double salt and the complex compound difference, we know that one, a complex compound has the special property that it does not dissociate completely into ions. The complex part will not dissociate. Here only which ion will produce? 1 Cl minus ion will produce. How much amount of AgNO3 you are adding? Irrespective of that, only 1 Cl can produce. That is why 1 AgCl. If they are giving 2 moles of AgCl, then you have to take 2 Cl outside. Here anyway it will not. If they are asking such a question, they will give NH3 as 5. Because inside the coordination sphere for cobalt it will be normally 6. Hope you understood this formula. They are asking IUPAC name. I am not going to write that because we have done so many questions. I will go for the next. Stability of compounds and the application. This is the last part of the chapter. So almost all topics we covered. Yeah, name already, already came. Good, well. Yeah, I think all you are confident in almost all part of chemistry, inorganic, physical and organic. Okay, fine. So we are expecting 100 out of 100, okay, this year. So which is more stable complex? See, which is more stable complex? CO, En thrice 3 plus. Here En is what? A chelate ligand. What is chelate or chelate ligand, you know? So a chelate ligand or chelate, you can pronounce, that ligand forms a stronger complex due to that cage-like structure. So that complex chelate, when En or EDTA is there, that will be more stable than monodentate ligand. So which is more stable complex? Only they are asking. This is more stable complex. You can write due to chelate effect. Yes, chelation effect or chelate effect, correct, well done. Give two examples. This is one question I took from the applications of complex compound. You know that one, applications of complex compound is there. Any one question they can put either in MCQ or normal question. So that's why I kept one question based on that one. Don't ignore that part. Right, give two examples of coordination compounds that are useful in analytical chemistry. You know what is analytical chemistry? Analytical chemistry means for identifying ions. For salt analysis we did. Yes, we have so many. I'll write two. Okay, two examples. You know that one, copper ion, Cu2 plus ions are identified by using which ligand? Ammonia. So if you are adding excess ammonia to copper, you know that one, deep blue precipitate, all we learned. So when NH3 is added to Cu2 plus, you will be getting NH3 4 times coordination sphere 2 plus. What is the color of this one? Deep blue. So if you are getting deep blue color, then it is confirmed that Cu2 plus ion is there. That is called analytical chemistry analysis. Okay, qualitative analysis, same. This is the first one. Second one, I'll write nickel. Ni2 plus can be identified by DMG. It is there in the textbook or reader. Dimethyl glyoxime. It's a didentate ligand. Dimethyl glyoxime is when added, it's a ligand when added to nickel ion. Okay, this test is not there in the lab. So Ni with DMG only you can write dimethyl glyoxime twice, complex compound with what will come 2 plus. What is the color of this one? We have a scarlet red color. Okay, or light red color or precipitate we will be getting. So by that way we can identify that. Yes, rose red is correct, Hiba. Yes, so scarlet red or rose red you can write, that is the color of this one, so DMG. Okay, so I think almost all topics we covered from this chapter. These all are the category of question, type of question you can expect. So once again you practice all these question. DMG is not deleted, that application part is there. See, DMG they won't ask any other question related to this one, or if you want you can write this one. If you can't remember this one, you can write the Brown ring test. Okay, Brown ring test you can write. Okay, Brown ring Fe, H2O 5 times, NO2 plus 2 plus, that also you can write. Okay, so doesn't matter, Brown ring test complex, the formula we are learning, no, that also you can write. DMG is just a ligand, they won't ask anything other than that. Yes, not tolerance. There is no relationship with the tolerance. Tolerance is different. Ammoniacal silver nitrate, that is different. This is DMG is a ligand. If you want the formula I will write, but that is only for entrance. Here you keep in mind, it's there in the textbook reader. Second one as DMG, when you are adding to this one you will get scarlet red. That you remember anyway. If they are asking two, you remember this one. Only one means this one. Fine. See, almost all topics we covered. I think it's fine. This is the same way we are going to continue for the next chapter. Yes. Is it fine? Hope you all got idea about the type of question what they are going to ask for complex compound, means coordination compound. Is it fine? Same way we will continue for the next chapter. Okay, fine. Okay. Yes, Nidin. Okay, fine. Okay. Yes, note it down, important point. Yes, Albert. Yeah, clear, good. So, yes. So, now these question from this chapter is over. Now we will go for D and F block elements. Yes, Arvind. Now it is D and F. Oh, yeah, fine. So be ready. Okay. T and F is quite interesting, right? It's more interesting than coordination compound or not? You guys like the chapter coordination? D and F block elements? Yeah, biomolecules also will come. Wait. I'll finish. Don't worry. Most of the question. Answer is coming as no. Dhruvil. Let's see. At the end of we will do our level best to solve almost all question. Yeah, it's anyway theoretical chapter. I know. Yeah. Okay. Let's see. We can try our level best to get few questions. That would be better. Okay, anyway, don't waste time. We will go to the question. Listen, not that tough. Okay, yeah. Electrochemistry also based. We don't have that much time. Okay, we will do this DNF and biomolecules we have under inorganic. Let us start. Don't frustrate. Let's try. So listen carefully. What all important points you note it down. Let us try anyway. Day after tomorrow is our exam. Your exam. So what all questions you are getting, note it down and try your level best. That is the thing we can do in the final lab. See, question is following ions are. Topic 1 is transition elements. You know that one, the major part question from this chapter will come as a reasoning question. You know that one, what is reasoning question. So transition element, I kept almost all type of question that you practice, then I think you will get. Yeah. Coming, the answers are coming. Hiba. Following ions are given. Cr2 plus, U2 plus, Cu plus, Fe2 plus, Fe3 plus, Mn3 plus. Identify the ion which is a strong reducing agent. Answer is here few confusion might be there definitely. Anyway, I'll tell the answer and I will explain. That would be better. Here option A, answer is Cr2 plus. I'll tell you the reason. Not Mn3 plus. Cr2 plus will readily converted as what? Cr3 plus. How? By losing electron, 1 electron. And this process is called what? Oxidation. I'll write on short. Oxidation, species which undergo oxidation very immediately, that's called a reducing agent. Then you will be thinking that some other is also there. The same way Fe2 plus also can go as Fe3 plus. Not. Because here this is the right answer. Why? Because Cr3 plus is stable due to what? Cr3 plus is stable due to half-filled T2G. That is the most stable part. So you know that one Cr3 plus means we wrote no this one. Yeah. So Cr3 plus will be more stable due to half-filled T2G. How half-filled T2G will come? Half-filled T2G means you know that one Cr3 plus will come as what? 3D3. So 3D3 means T2G has 3. See 1, 2, 3. This is T2G. So that is the right answer. Yes. B. Unstable. See, if they are asking a question like this one for D and F, the same only will come. So here don't expect the another question like this one. No, this the same type only will come. So listen carefully and learn. So unstable in aqueous solution, definitely answer is what? Cu plus. That is why Cu plus unstable because of what? Less hydration enthalpy. That is Cu plus is unstable. That is why it undergo disproportionation to form Cu2 plus plus Cu. If you want to write the balance equation, we have a balance equation C2 Cu plus. Cu2 plus has what? High hydration enthalpy. Okay, high hydration enthalpy. That is why Cu2 plus is stable in aqueous solution. Cu plus is unstable because of low hydration enthalpy. Cu plus is unstable. That is they are asking in aqueous solution. So in aqueous solution, Cu2 plus is stable. C. A strong oxidizing agent. What is the strong oxidizing agent? Strong oxidizing agent is which one? I think it is Mn3 plus. Why? Mn3 plus will readily accept 1 electron. Mn3 plus will readily accept 1 electron and converted as what? Mn2 plus. Accepting 1 electron means that process is called what? Reduction. And reduction, undergoing reduction means what? Strong oxidizing agent. They are asking reason, that's why I am explaining. Mn2 plus is why stable? Because of half-filled D. Half-filled D orbital. Okay. So we have half-filled D orbital. Because of half-filled D orbital, it is more stable. So answer I wrote Mn3 plus here Cu plus and Cr2 plus. Yes, half is correct. Cr2 plus. Second one is Cu plus, that you did not get. Albert, correct. Cu plus, and third one is Mn3 plus. Fine. Hope you got. The same type of question only will come. So here, see, whenever T2G and half-filled D comes, keep in mind which is more stable, half-filled T2G. Yes, Aravind. Second one is Cu plus and Cu2. This one you remember right now. no need to go for any concept. Cu2 plus means what? There is high hydration enthalpy which can compensate the second ionization enthalpy, because Cu2 plus means you know that one. Okay, Cu electronic configuration is what? Cu plus electronic configuration is what? 3d10 4s1. One more electron has to remove from this one, that is second ionization enthalpy. That can be compensated by high hydration enthalpy. That is the way Cu2 plus is stable in aqueous solution. But whereas Cu plus is not. Cu2 plus when happen, Cu2 plus is smaller ion, more solvation enthalpy, that we learned. Smaller the ion, more solvation enthalpy. Solvation means hydration enthalpy. That is the way it is stable. Question number 2. Give reason. This is the another type. The same type of question. Yeah. E naught value for Mn3 plus to Mn2 plus. See, same question only they will ask if they are asking this type of question. Okay. So Mn3 plus to Mn2 plus couple is much more positive. So it's simple. The logic I will explain first. E naught value they are saying much more positive means, keep in mind it is spontaneous. Spontaneous means what? They are saying that Mn3 plus will accept one electron and readily converted as Mn2 plus. That is a question they are asking. Because E naught value positive, which means it is spontaneous. Spontaneous means this will take place immediately. It's correct. Why? Because the reason we know already, that is half-filled D. But the question they are asking in a different way. That's why I put this one, half-filled D orbital. So Mn3 plus to Mn2 plus couple is much more positive. But at the same time, Fe3 plus to Fe2 plus, they are saying it will not go. Much more positive, okay, than this one. This one it will not. Why? Because Fe3 plus 2 plus Fe3 plus will accept one electron and when converted as Fe2 plus, this is non-spontaneous. We can say. Why non-spontaneous? Because this is more stable. So from stable state, it will not be ready. It will not be ready to transfer as Fe2 plus. So Fe3 plus, what is the electronic configuration? You know, it is 3d5 4s0. Because you know that one, it is 3d6 4s2 normally. So Fe2 plus means it is 3d6 4s0. Fe3 plus means what? It is 3d5. Okay. So it is 3d5 4s0. This is more stable because of what? Half-filled D. So from half-filled stable D, it will not change. So that is the reason. So you have to say that Mn2 plus is more stable due to half-filled D orbital, whereas Fe3 plus is more stable due to half-filled D. Yes, that is why this reduction will not take place easily, but here the reduction will take place very readily. That is why more positive, this is less positive. Hope you understood. Now we will go for question. Yes. Now we will go for the question B. Sub question B. What is the question? Iron has higher enthalpy of atomization than that of copper. You know, enthalpy of atomization is based on, yes, half is enthalpy of atomization is based on what? Number of unpaired electron and metal-metal bond. So if a metal has strong metal-metal bond, then it will have higher enthalpy of atomization. Strong metal-metal bond will be formed if there is unpaired electron. More number of unpaired electron means what? More stronger metal-metal bond. More stronger metal-metal bond means that you have to provide more, or you have to supply more energy to separate these atoms, as means these metal atoms. That is called enthalpy of atomization. So what you need to tell? Iron has higher enthalpy of atomization because iron has more number of unpaired electron. Fe, what is electronic configuration? 3d6 4s2. What about copper? Copper is 3d10. Okay, 4s2. Sorry, 3d10 4s1. Yeah, 3d10 4s1. Then you know that one here, no unpaired electron. In case of copper, here how many unpaired electrons will be there? 4. 3d6 means you know how to arrange, right? So 1, 2, 3, 4, 5, 6. How many unpaired electrons are there? 4. So iron has 4 unpaired electron. Yes, whereas copper has no unpaired electron. More the number of unpaired electron, stronger the metal-metal bond, more is the enthalpy of atomization. That terms only you need to write. No need to explain in so much words and all. These points you need to write in chemistry. Then you will get the mark. Yes, Arya Trivedi. Yes, tell. So that is the iron has higher enthalpy of atomization because more unpaired electron, then stronger metal-metal. Then we will go for sub question 3. Scandium 3 plus. Scandium 3 plus is colorless in aqueous solution, whereas Ti 3 plus is. See, again, color is based on what? Unpaired electron. Color is based on what? Unpaired electron. So how do you write scandium? Scandium is 21. Okay, 21 normal electronic configuration is what? 3d1 4s2. So scandium 3 plus means what? 3d, yes, 3d 0 4s0. There is no unpaired electrons in D because scandium is 3d1 4s2. So scandium 3 plus means the electronic configuration will be argon. Okay, before argon only will come. There is no unpaired electron in D. So you have to say that no unpaired electrons in D subshell. Whereas Ti 3 plus, you know that one, titanium 3 plus. What is the atomic number of titanium? Titanium is 22. General electronic configuration is what? 3d2 4s2. So 3 has gone. So what is 3d1 4s0? 3d1 means one unpaired electron is there. One or more doesn't matter. Unpaired electron is there means definitely color will be there. So you have to say that if scandium 3 plus has no unpaired electron, so no DD transition, no color. This Ti 3 plus has one unpaired electron, so DD transition, color. These points only. Yes. Yeah, Nitin, correct. Yeah. Now we will go to next question. Account for the following. Yes, account for the following. This is what I told you. Reasoning questions you can expect. So many reasoning questions based on transition elements only. So transition elements. So this chapter, if you are going to get question, most of the question will be reasoning. Okay. And one preparation question is there that I will teach you. So why transition metals have large number of complex compound? Only point I will write. Okay. So why transition elements can form large number of complex compound? Due to small size. Transition metals have small size. After that, high charge, or high charge means high positive charge. High positive charge, small size, and availability of vacant d orbital. So these three are the reason behind the formation of large number of complex compound by transition elements. Their small size, due to high charge, they have small size, and vacant, so many vacant d orbital. That's why ligands can donate lone pair of electron. That's the way they are forming complex compound. Hope you understood. B. What is B? Transition metals and their compounds are generally found to be good catalysts. Very repeated word. So they act as good catalysts. Which one? Transition metals. Why? Because they can form reaction intermediates. What is that? They form reaction intermediate. Intermediate means, you know that one chapter has been deleted actually, surface chemistry. There we actually, this reaction intermediate means it combines with the catalyst to form reaction intermediate. Yes, due to variable oxidation state. Yeah, exactly. They form reaction intermediate due to variable oxidation state. Okay, variable oils. And one more is there. What? They provide surface area. Surface area for what? Adsorption. Because normally the reaction takes place by adsorbing the reactant molecules on the surface of a catalyst. So these catalysts, when transition elements or transition metals acts as a catalyst, they will have larger surface area. That large surface area will help for more adsorption. So they can provide surface area for adsorption. They form reaction intermediate due to variable oxidation state. Aravind. B, right? Yes. They form reaction intermediate means before actual product an intermediate will be produced, because they can change their oxidation state. That's called variable oxidation state. So if there is a possibility of showing different oxidation state or variable oxidation state, then reaction intermediate can be formed easily. And one more point, they can provide surface area for adsorption, because reaction takes place on the surface of a catalyst normally. So catalyst has more surface area means more reactant molecule can adsorb on the surface. That these transition metals can provide. These 2 points you need to write, then only you will get complete mark. Third one, zinc is a comparatively soft metal, or you know that one, zinc is considered pseudo transition metal, same, because it has completely filled what? Completely filled d orbital. Okay, completely filled d orbital. Yes, so completely filled d orbital means no metal-metal bond. Okay, metal-metal bond will not be there. No metal-metal bond. Why? Completely filled d orbital cannot form any metal-metal bond. No metal-metal bond means they are soft, because strong metal-metal bond. Chromium. What about chromium? Chromium has maximum number of, okay, Cr has maximum number of unpaired electrons. maximum number of unpaired electrons. So strong metal-metal bond. So strong metal-metal bond will be formed by chromium because of maximum number of unpaired electron. Yes, there is no metal-metal bond. Not better you should write metal-metal bond, because two adjacent metal atoms make bond between. Yes, pairing by taking the pair of electrons. So you should write metal-metal bond, and that is strong because of maximum number of unpaired electron. That is why that is a typically hard metal, chromium. The sub-question 4. D. What is the sub-question 4? The enthalpy of atomization of transition metals are quite high. Here the same reason is there, but the repeated one, that's why I put. Because of unpaired electron and strong metal-metal bond. Yes, why they form transition metals have high enthalpy of atomization? Because of unpaired electron. So when unpaired electrons are there, they can form what? Strong metal-metal bond. Strong metal-metal bond. So if they form strong metal-metal bond, the enthalpy of atomization will be large. I told you. Unpaired electron, and they form, yes, strong. Yes, half is that the right way you have to present the answer. Okay, fine. We will go to question number 4. I think it's visible. Okay. So here they are giving the value chromium. The electrode potential value is given, Mn electrode potential value, iron, cobalt, nickel and copper. The question is, from the given data of E naught value, answer the following question. Why is E naught of Cu2 plus Cu value is exceptionally positive? You know that one, stability of oxidation state depends on two factors. Which all? Stability of oxidation state depend on three factors. Which all are there? First one is atomization enthalpy. Enthalpy of atomization or atomization enthalpy, same only. Enthalpy of atomization. Second one is what? Ionization enthalpy. Ionization enthalpy. Third one is what? Hydration or solvation enthalpy. See, these three factors determines the stability of due to filled orbital. Hiba, that is not the right way to give the answer for this one, because here they are asking about the E naught value. Why the E naught value is coming more? Which means that oxidation is Cu2 plus value is Cu2 plus 2 Cu. Okay, the value is exceptionally positive, means you have to tell the answer like this one, because the stability of an oxidation state depends upon atomization enthalpy, ionization enthalpy and hydration. You know that one. Here the enthalpy of atomization is what? Positive, because we are supplying energy. Ionization enthalpy is even what? Positive, but hydration enthalpy is what? When an ion dissolves in water, it liberates energy, that is hydration enthalpy, that is negative. So in such a question, if they are asking in any case, if the E naught value is positive, means you have to say that the sum of the first two will be large value or more, you can say. So if they are asking, because you know that when these two are positive and this is negative, so when you are taking the sum and you are getting a positive value, which means the first two are higher than that of the hydration enthalpy. Yes, so how will you give the answer? Here you have to say that for copper, enthalpy of atomization and ionization enthalpy is much higher than which one? Hydration enthalpy. Okay, because you know that one, copper has an electronic configuration. No, copper has an electronic configuration what? 3D 10 4s1. Here definitely will be IE1. What is IE1? First ionization enthalpy. Then IE2 will be quite large. So first ionization enthalpy anyway will be less. Sum I am taking. The sum of these two will be very high. Okay, and the atomization enthalpy, when you are taking together, that value will be quite large. When which one? Hydration enthalpy. So answer is, yes, half is. Answer is sum of enthalpy of atomization and ionization enthalpy is much higher than the hydration enthalpy. That is why positive. Then you will be able to write the answer for the next one. That logic you understand, then you will be able to answer the why value is negative. E naught of Mn2 plus / Mn value is highly negative. You have to say that here, why it is highly negative as compared to other elements, because for Mn, you know that one, Mn, what is the electronic configuration? Electronic configuration is 3d 5 4s2. So here the first two electron will easily remove. Why? Because 3d 5 is more stable. Therefore, here we can say that the sum of the first two will be very less, because actually they want to be like 3d5. If it is 3d5, it will be more stable. So for Mn, you can say that the enthalpy of atomization or atomization enthalpy and the ionization enthalpy value is very less, and hydration enthalpy is high. That is why negative came. Hope you understood. Yes, correct. The third one, which is a stronger reducing agent, Cr2 plus or Fe2 plus? I think I gave the answer already. Cr2 plus is stronger. Why? Cr2 plus readily converted as Cr3 plus by losing one electron. Okay? Because Cr3 plus is more stable due to half-filled T2G. What T2G? Half-filled T2G. Yes, correct. And Fe2 plus can also converted as Fe3 plus, but that is half-filled D. So when you compare the stability of half-filled D and T2G, which is more stable, T2G is more stable, because that splitting energy is there. Splitting energy comes means that is more stable. So Cr3 plus is more stable due to half-filled T2G. Yes, Dhruvil. Aqueous is not mentioned. Yeah. Hydration enthalpy considered when, aqueous is not mentioned. Yeah, in hydration enthalpy, because that ion when dissolves in water, then only we will cut. Yes, correct. So these two cases you consider in case of copper. The first two, wherever they are asking positive, you keep in mind the sum of the first two will be large than the hydration. Wherever it is coming as negative in case of Mn, that's I told you, Mn the first two will be very less, because Mn2 plus is more stable. So actually it want to go like Mn to Mn2 plus, not like Mn2 plus to Mn. So Mn to Mn2 plus is more positive, that's why it's negative. Here they are asking Mn2 plus to Mn, that is why negative. If it is Mn to Mn2 plus, it will be positive. Hope you got. Okay, fine. Question number 5. Account for the following. Here I think you will be able to answer it. I put this question because it's a repeated type. Read the question. E0 value of Mn3 plus to Mn2 plus couple is highly positive. Now you can tell why. Because Mn3 plus will readily turns as Mn2 plus because of half-filled stability of d orbital. Okay, half-filled stability of half-filled d of which one? Mn2 plus. Whereas Cr3 plus to Cr2 plus, it will not go. That is they are asking as compared to Cr3 plus, because Cr3 plus is more stable due to half-filled T2G. Okay, half-filled T2G. So here half-filled T2G is there, and here half-filled D is there. So Mn3 plus will have the tendency to change, but here Cr3 plus will not have the tendency to change as Cr2 plus. Cr3 plus is more stable. Yes, more stable due to half-filled T2G. Yes, Nitin. Now we will go for B. Which of the following cations are colored? It's quite easy. Which of the following cations are colored? Sc3 plus, no need to write because argon. No D. D is 0. Anyway, vanadium 3 plus. What is the atomic number of vanadium? Vanadium is 23. So you will be getting 3d2 4s0, because normally it is 3d3 4s2. Okay, so here it is 2 unpaired electron. 2 unpaired electron means it exhibit color. After that Ti4 plus, I think we already wrote this. Ti4 plus means what? It is 3d4 4s2, so it is 3d2 4s0. Titanium is 22, so 3d2 4s2, so 3d0 4s0. Titanium is 22, 4 plus means no unpaired electron, 0. Which of the following cations are colored? Mn2 plus. So Mn2 plus means what? 3d5 and 4s0. So it has 5 unpaired electrons. So these two are colored. Okay. So this is colored and this is colored. Correct. Vanadium 3 plus is colored and Mn2 plus is colored. Good. Fine. Over. Now we will go to question number 6. Transition metals show variable oxidation state. Another repeated one. Reasoning question. This type of so many reasoning question you can expect. Why why transition metals show variable oxidation state? You know, so that one transition elements show variable oxidation state because n-1d and ns orbitals have comparable energy. Comparable energy means, you know that one, They have almost same energy. So electron can participate in reaction from n-1d as well as ns. Not unpaired electron, the energy between, yes, the energy between the ultimate and the penultimate. If you are saying like that one, it's fine. Or you can write this way, n-1d and ns. This is the ultimate and this is the penultimate. That way you can say, tell if you want. Okay. So the ultimate and the penultimate has same energy. I wrote in a different way, n-1d and ns generally has same energy. Yes, that is why electron can participate from both. That is why so much variable oxygen state will be there. Zinc, cadmium, mercury are soft metal. The same I explained. Okay, these are soft metals because they have completely filled d. Completely filled d. So completely filled d orbital. Okay, so completely filled d orbital means there is no metal-metal bond. There is no metal-metal bond means soft. Okay, no metal-metal bond. Metal atoms, adjacent metal atoms or atoms will not be bonded. Sub-question B. What are interstitial compounds? Write their properties. Another important one. Yes, what do you mean by interstitial? Interstitial compounds means transition elements have an ability to form interstitial compounds. So what are interstitial compounds? Okay, non-metals like or small elements like means the based on the size. Okay, non-metals like carbon, nitrogen, hydrogen, etc. can be trapped into the interstitial sites of transition elements. Such compounds are called what? Such compounds are called interstitial compounds. So some for example, carbon can take nitrogen. Okay, like that. So some element, transition elements, carbon and nitrogen can be trapped. So non-metal elements like carbon, nitrogen, hydrogen can be trapped in the interstitial sites of transition elements. Such compounds are called interstitial compounds. And what are their chemical properties? They have high melting and boiling point. High melting and boiling point. They are electrically conducting. Electrical conductors, or they become conductor when these non-metals elements like nitrogen, hydrogen is trapped into the interstitial site, and they are chemically inert. They are chemically inert. These many things you keep in mind. So they have high melting and boiling point. Compounds when smaller elements like carbon, nitrogen, oxygen occupy in the interstitial sites of transition elements. They are called interstitial compounds. So yes, they are chemically inert. They have high melting and boiling point. They are electrical conductors. Aravind, definition of interstitial compound means transition elements have ability to absorb or trap non-metals like carbon, nitrogen, okay, or hydrogen, etc. into their interstitial sites. Means the gap between atoms or gap between metals. Yes. Now question number 7. Question number 7 is how would you account for the following? Another, metal-metal bonding is more extensive in the 4D and 5D series of transition element than 3D. Another question. Can you answer to this? Metal-metal bonding is more extensive. What they are asking? So we have 3D series, we have 4D series, we have 5D series, isn't it? So that 3D, 4D and 5D series, when you go through these series, 4D and 5D series have more stronger or more frequent metal-metal bond. Why? No, not Lanthanide contraction. We did not even reach that topic. This is transition elements only. See, they are asking about transition. 3D and 4D means, not because of that, I'll tell you. See, 4D and 5D has what? Larger size. Larger size. Or they are more exposed to space. We can simply say 4D and 5D has larger size. Because of larger size, the electrons in 4D, the outermost shell of 4D and 5D, electrons in 4D and 5D are loosely held by the nucleus. You know that one, if orbitals are away from the nucleus, electrons are loosely held. Electrons are loosely held by the nucleus means they can form frequent metal-metal bond. Energy levels of, no, correct answer is 4D and 5D has larger size or they are more exposed to space. Either of the way you can tell. And the valence electrons are loosely held. Okay, by the nucleus, so they can form more frequent metal-metal bond. more frequent. Yeah, that also you can tell. Poor shielding effect. That is why electrons are loosely held. In 4D and 5D, electrons are loosely held. Therefore, they can form more frequent metal-metal bond. That is the reason they have larger size. I mean, due to larger size, they have more frequent metal-metal bond than 3D. I'll go to the B. Mn3 plus undergo disproportionation. That is quite easy. Mn2 plus is more stable due to what? Half-filled D. Due to half-filled D. See, logic is same. The way they are asking, you understand and write. Electrons can form metal-metal bond as they are placed extensively. Yes, half is 4D and 5D has larger size, so valence electrons are loosely held in 4D and 5D. So that loosely held electrons can form a more extensive metal-metal bond. Hope you got. Okay. Mn, I told you, Mn3 plus readily turns as Mn2 plus. That's the disproportionation. Means they change the oxidation state. That's it. Very readily, because Mn2 plus is more stable due to half-filled D. Most of the transition metal ions exhibit characteristics color in aqueous solution. Easy. What is the reason? Transition metal exhibit color in aqueous solution because of unpaired electrons in D subshell and goes DD transition and undergo DD transition. So if they are asking color, world of arts and crafts, repeat what I should need to repeat. Yeah, this one, right? For A, sub question A, 4D and 5D has larger size, electrons are loosely held, so they can form more frequent metal-metal bond than 3D. The last answer, unpaired electron DD transition. Most of the transition metal ions exhibit characteristic color because of unpaired electrons in the d orbital and DD transition. No unpaired electron means no DD transition, no color. Fine. Question number 8. Yeah, this is the another question from previous board. A graph is given. It's easy only. I think it's visible. Okay. So here the question is, see, 3 series are given. One is starting from titanium vanadium, that is 3D series. Zirconium niobium, that is 4D series. This is 5D series, that is 3D, 4D, 5D. Why manganese has lower melting point? That is quite easy. You know why manganese has lower melting point? Because Mn has half-filled D. 3D 5 4s2. Default half-filled D is there, means it will not make metal-metal bond. So we can say weak metal-metal bond will be formed because it's already stable because of half-filled D. So Mn has half-filled D, therefore weak metal-metal bond. That is why weak metal-metal bond means what? Lower melting point. That is why you know that one exceptionally low. Melting point is given over here, okay? It's exceptionally low melting because here it is melting point, okay? MP is taken over here. Here it is atomic number. Okay, so correct answer for the A. B. Why do transition metals of 3D series have lower melting point as compared to 4D series? You know that one 4D series have more loosely held unpaired electron than 3D series. Okay, so why do transition metals of 3D series have lower melting point? Because you know that one, as I told you here, yeah. So in the 3D series, electrons are in 3D and 4D they are asking. The other one is a different version. Here it is different. Why do transition metals of 3D series have lower melting point? So lower melting point means what? Their weak metal-metal bond. Here as compared to melting 4D, the same only I told you. Yeah, 4D means what? They make more frequent metal-metal bond. So more frequent metal-metal bond means stronger metal-metal bond. Stronger metal-metal bond means melting point will be high. Because they are talking about melting point again. This one. That is the graph given. In the third transition series, identify the name of the metal which has the highest melting point. That is this one. Which one? W. Which is the element W? Hello, all of you are there, I think. Yeah. Send your answer. What is W? Yes, tungsten. Ah, good, good. Alvin. Tungsten. Alan, Joseph. Yes, W is tungsten. So tungsten has the highest melting point because maximum number of unpaired electrons. Second answer, 4D series makes more frequent metal-metal bond. Wherever they are asking higher melting point, you write this. It forms more frequent metal-metal bond, therefore higher melting point. Manganese has already filled D, so weak metal-metal bond. Okay, so lower melting point. So this question is easy. So read the question. The logical wise the question they are asking will be same. So understand the question or the logic. Okay. So I think we have few more questions. Topic, yeah. Now the reasoning question got over. Yes. Now the reasoning question got over. Topic, preparation of K2Cr2O7 and KMnO4. You know that one preparation part is important. So here they are asking the question indirectly. Read the question. This was there in the previous board. A mixed oxide of iron and chromium, it's given FeCr2O4 is fused with Na2CO3 in presence of air to form yellow colored compound. A. That on acidification, compound A forms an orange colored compound finally B, which is a strong oxidizing agent. We know that one. This is they are indirectly asking to write the balanced equation for the preparation of what? Yes, K2Cr2O7, because they are saying finally orange color. Orange color means which one? Not Na2Cr2O7. Orange color is anyway K2Cr2O7. Yes. So how do you write the preparation reaction? So preparation reaction, the balanced equation you need to learn. I will give an easy method. So what is going to react? Step 1. Okay, in the step 1 reaction, FeCr2O4, that is called chromitor. This one, oxide of iron and chromium, it will be combining. So FeCr2O4 when reacts with which one? Na2CO3 and oxygen, air. What you will be getting? You will be getting Na2Cr4. Okay, sodium chromate, not dichromate, sodium, Na2Cr4 plus Fe2O3. Fe2O3 plus CO2 will come because carbon and oxygen will come. So Fe will combine with oxygen to form Fe2O3, Na2Cr4 will come, and this is the one. It should be balanced, they are asking. See, right? So I'll give an easy method. Okay, for exam, for scoring mark, this is the method you keep in mind. Otherwise, while writing the equation, balancing is quite difficult. So you remember this code. Okay, 487 means digit you remember 487, which means here it is 4, here it is 8, here it will be 7. Okay, so you will be getting, yes, so this one you keep in mind 487, which means 4 Fe2. So here I should add 2 Fe2O3, here 8, so I should add 8 Na2. Then you know that one, how many carbon is there? 8 carbon. So I will balance. Now the balanced equation we got for the first step. What is the step 2? Step 2, they are saying this will, which one? The compound what we got, here it is. Okay, Na2, yes, Na2Cr4 will be acidified. Okay, yes, Na2Cr4 will be acidified, means we will be adding an acid. Then what will you get? You will be getting an acid. It's 2 Na2Cr4 you can take. So Na2Cr2O7, it will be converted as sodium dichromate, and you know that one, this 2 Na plus will come out, because 2 Na plus means you know that one, that will be substituted 2 Na plus. Okay, and 2 H2O will come, because 2 molecules, then only it will be balanced. I think this is balanced. It's quite easy to balance. 2 Na2Cr2O7, 2 Na plus came, that's why I put over here. Then 2 H2O means here we have to write 4. Okay, so it will be 4H plus. I think now it is balanced. Step 3, one more is there. What is the step 3? Step 3, the formation is, you know that one, this Na2Cr2O7, this preparation you have to learn. Na2Cr2O7 when reacts with the 2KCl. Okay, so it will be getting what? K2Cr2O7, potassium dichromate will be coming. After that 2 Na and 2 Cl combined to form 2 NaCl. Now we have balanced equation. You got or not? This is the preparation of which one? Preparation of potassium dichromate. What is the color of this one? Orange. You know that one, we have 2 ion. One is what? Cr2O7 2 minus. The color of this ion is orange. In basic medium, it converted as CrO4 2 minus. What is the color of this one? Yellow. This one also they asked in board exam. Keep in mind. And CrO4 is stable only in basic medium. The Cr2O7 is stable only in acidic medium, which means H+. In acidic medium, Cr2O7 will be stable. Basic medium, CrO4 2 minus is stable. This one you learned, right? Yeah, half is. I wrote the complete equation because they are asking orange colored compound. Okay, orange colored compound. That orange colored compound is which one? K2Cr2O7. Yeah, in question normally if they are asking these three equation you need to write, then you will be getting 2 marks. Anyway, I wrote the complete preparation because this is important. Preparation one question you can expect. FeCr2O4 Na2CO3 plus 7. Yeah, this question, yes. Yes, it's orange. K2Cr2O7, it's orange color. And here it is yellow, CrO4. That orange colored one, Cr2O7 2 minus is stable in acidic medium. CrO4 2 minus is more stable in basic medium. Dichromate ion is orange. Yeah. In this question, if you are stopping the second step, you will get the mark. Okay, I got here. Because I wrote the complete step because if they are asking for complete preparation. Yeah, Cr2O7 2 minus anyway, it's a orange colored one. Yeah, half is. So this one, this itself is orange because Cr2O7 2 minus is. I wrote because potassium dichromate, they may ask for preparation. Okay, we will go for next one. See, this type of one question you can expect. What is this one? It's complete the reaction. Yes, complete the reaction Cr2O7 2 minus. You know that one, it's a strong oxidizing agent. That is what we learned in the previous question also. They said Cr2O7, okay, Cr2O7 2 minus ion. When combines with I minus ion, you will be getting what? Cr2O7 2 minus will converted as Cr3 plus. It itself reduced to form Cr3 plus. I minus converted as I2. H plus anyway we can ignore because we are going to balance in acidic medium. How to balance this one, you know, right? Here the oxidation state of chromium is what? Plus 6. And here it is plus 3. Oxidation number method I will use. Here 2 chromium is there, so we have to put 2 chromium over here. So the difference is what? 6. Here to here. I minus means minus 1. Here 2 is there, so I will put 2 I minus. Minus 1 and here it is 0. So minus 1 and 0 means difference is what? 2. Okay, minus 2, here it is minus 2 and 0. So this 2 should be multiplied with the 3. Then I will be getting the answer Cr2O7 2 minus plus 3 into 2 is 6. 6 I minus gives 2 Cr3 plus 3 I2. After that, you know how to balance oxygen. 7 oxygen means no oxygen over here. I will add 7H2. 7H2 means 7 into 2, 14 hydrogen. So I should add 14H plus. This is the balanced equation which shows the oxidation property of dichromate ion. So Cr2O7 2 minus will oxidize I minus to I2. That is the complete balanced equation. It's important. Important means this type of one question for the complete the reaction they can ask. Okay, so this is the answer for A. What is B? B is MnO4 minus. That preparation we will learn. MnO4 minus plus, okay, NO2 minus. So if it is NO2 minus, MnO4 minus is a strong oxidizing agent again. It oxidizes NO2 minus to what? Acidic medium. It will convert it as Mn2 plus NO3 minus. MnO4 minus itself, it's an oxidizing agent, undergo reduction to form Mn2 plus. NO2 minus is oxidized as NO3 minus. You know how to balance this one, right? So balancing means here it is plus 7. Here anyway plus 2. Here NO2 minus means that one. Oxidation state will be what? Here it will be minus 2 into 2, minus 4. Minus 4 become plus 4. Here it will be plus 3. Okay, so here you can write plus 3 and here it will be plus 5. Understood. Now you have to take the difference. So 7 to 2, the difference is what? 5. Here 3 to 5, difference is 2. So you know that one, you should multiply vice versa, 5 into 2 and here 2 into 5. Anyway, acidic medium only. I'm not going to explain this one because you know that one the same way you have to do. Here you multiply, after that equalize oxygen. In which side it is deficient, there you add water. When you are adding water, how much hydrogen is coming extra, that much H plus you add on the opposite side. This type of complete the reaction question they can ask. MnO4 minus in acidic medium, always Mn2 plus. Cr2O7 2 minus in acidic medium, always will give Cr3 plus, because it shows the oxidizing property of K2Cr2O7 as well as MnO4 minus. Okay. Now the last one, I think we have one more topic. This is the preparation of which one? KMnO4. Either the KMnO preparation or K2Cr2 or K2Cr2O7 preparation they can ask. Okay, listen. So KMnO4 preparation means you know that one steps involved for the KMnO4 from pyrolusite. So from pyrolusite, what is pyrolusite? Pyrolusite ore is what? MnO2. Okay, so MnO2 when reacts with the potassium hydroxide and oxygen, you will be getting what? You will be getting K2MnO4. You know what is K2MnO4, right? K2MnO4 is what? Potassium manganate. And okay, potassium. So here also you can remember the balanced equation. Here it will be 2MnO2 plus 4 KOH. Okay, so you will be getting K2MnO4 plus 2H2O. Okay, K2MnO4 plus 2H2O. That is the reaction from pyrolusite ore, that is MnO2. Second step, you know that one, that K2MnO4 means nothing but it is MnO4 2 minus. MnO4 2 minus can be electrolyzed easily. Electrolysis, different method is there, disproportionation and electrolysis. This is easy. If you are passing electricity through MnO4 2 minus, you will be getting MnO4 minus plus 1 electron will come. This is called potassium permanganate. So this is the preparation. Guys, are you there, right? All are. Now D and F, as you said, D and F is not that interesting. Means the some theoretical part will come. That reasoning question and all over. Now we have the preparation methods of, yes, Faris, yeah, Hiba. Okay. Fine. Anyway, we will wind up this one within 5 minutes. After that, I need a half an hour extra. Okay, then we will wind up biomolecules. Okay, let's see, we will finish this one. After that, let us see. Okay, so this one is the preparation method of which one? KMnO4 minus. So don't ignore any part, because it's a complete chapter, means from anywhere the question can come. So prepare thoroughly all the possible question you practice. This is the preparation method. One more question we have from this chapter, all the topics we came across. This is lanthanides and actinides. So here so many questions are there. Okay, I select so few selected questions are here. Important one, what is lanthanide contraction? Another important one, what is lanthanide contraction? Lanthanide contraction is a gradual decrease in size from lanthanum to lutetium. You know that one, lanthanum or lanthanide start, after lanthanum cerium comes, cerium to lutetium. You can say from lanthanum to lutetium there is a regular decrease in atomic size due to poor shielding effect of 4f electron. Which electron? 4f electron, or you can say 5d subshell. That is also same, because for lanthanides the general electronic configuration is what? 4f, 5d and 6s. These are the orbitals involved in lanthanide. So 4f subshell, okay, or 4f electrons will give only poor shielding effect, which means 4f electrons are not giving any shielding effect to the inner 5d. So 5d electrons are not protected because of poor shielding effect of 4. Yes, 4f, yeah, that you can say. So there is a gradual decrease in atomic size from lanthanum to lutetium due to poor shielding effect of 4f electrons. That gradual decrease is called lanthanide contraction. And you know, two consequences are there. What is the two consequences? First one, similar atomic size of 3d and 4d elements, means elements in 3d and 4d has similar size. For example, we learned zirconium and hafnium. They did not ask even, okay, zirconium and hafnium has same size because of lanthanide contraction. And the basic property of lanthanum hydroxide to lutetium hydroxide decreases. Okay, we can go for the next one, europium. These questions are not that easy. Listen very carefully. NCERT exercise ka questions exam hote. Yeah, all the exercise question will come. Yes. Asta. Yeah, exercise question all you have to practice. Chances there. Yes. So why is europium is more stable than cerium? You know that one, cerium has electronic configuration. What is cerium? Cerium is the first element. So you have the cerium electronic configuration. Here it will be 4f. Okay, 1, 5d, 1, 6s2. So here, yeah, so here 5d 0. Yeah, so they are asking cerium, and cerium is the first element. Okay, cerium is the first element, I'll tell you. So why is europium? Europium means, you know that one, EU. Okay, EU has what? Half filled 4f subshell, that is 4f7 will come. Europium. In which oxide state? 2. Because Eu 2 plus means 4f7, 5d0, 6s2 will come. Because normal electron, 6s0, right? Okay. 6s0 will come because 6s2, 5d, europium, 4f7, 5d0, 6s2. So because of half-filled 4f, you know that one, half-filled 4f means it will be more stable. More stable than cerium. Cerium 2 plus means it will not be getting, because cerium plus 4 is more stable. Cerium plus 4 has what electronic configuration? Cerium plus 4 has 4f0. Okay, 4f0. 4f0 means, you know that one, the completely filled electronic configuration will be there. Cerium plus 4. 2 is not stable. So here, no need to mention cerium. You explain about europium. Europium always you keep in mind, europium 2 plus is stable, whereas cerium plus 4 is stable. This one always you keep in mind. Cerium plus 4 is 4f0. That only you can remember. Europium plus 2 is stable because of 4f7, half filled. That you keep in mind. Half filled. Same like another. Y is plus 3 oxide state of gadolinium. You know the symbol of gadolinium? It is Gd. Gd has half filled. Why? How half filled? It will be 4f7, half filled. Keep in mind. And what about gadolinium and lutetium? Lutetium will have a completely filled. Lutetium, what is the symbol? Lu. These 4 elements only you keep in mind. That only they will ask. Lutetium has electronic configuration 4f14. What? 4f14, because lutetium is the last element here, cerium to lutetium. Lutetium is the last element, so it has completely filled the 4f orbital. If they are asking about gadolinium, okay, Gd, you have to say that it has 4f7, half filled. Which one? Half filled. That is Gd 3 plus. 3 plus has 4f7, half filled half filled f subshell. Europium 2 plus has half filled f subshell. Keep in mind. Okay, ytterbium is there. That also in some case they asked. Ytterbium, YB 2 plus. Okay, also has that half filled. Either europium, ytterbium, cerium or terbium they will ask. Okay, so this europium has half filled for 4f subshell. Lutetium has completely filled 4f subshell. Gadolinium has half filled 4f subshell. That is why they are more stable. Why is actinoid contraction is greater than that of lanthanoid contraction from element to element? Tell the reason. Same like, yes, ligma, Johnson, ligma. This one, cerium to lutetium, the first transition series. In this cerium to lutetium, elements are coming. You know that one, gadolinium comes. Okay, lutetium is the last one, that I will tell you first, then you will get some idea. Lutetium is the last element, means 4f will be what? 14. Okay, so 4f will be 14. They're talking about lutetium plus 3, right? Both. So 4 complete I will write first. 4f 14, then 5d1, 6s2. This is the general electronic configuration of transition element. D will be 0 or 1. S will be 2. So this is the general complete electronic configuration of lutetium. You can check the periodic table. You have to remember this word. What about lutetium 3 plus? 3 plus means these 3 electron will be removing. Then what I will get? 4f14. 4f14 is what? Completely filled F. Completely filled F is stable. Same like I will tell you gadolinium, Gd. Gadolinium, what is the electronic configuration you are going to get? 4f. It's the 8th element actually. Okay, 4f8, 5d0, 6s2. This one anyway you have to remember, otherwise from atomic number and all you won't be able to write. 4f8, because this is the 8th element. Okay, so 4f8, 5d0, 6s2. What they are asking, Gd 3 plus. How many electron you have to remove? 3. S from S I will remove 2, and from 4f I will remove 1. Then I will get 4f7. 4f7 means half filled F. Same like half filled D and completely filled D, we have stability for F also. So this is completely filled F, stable. This is half filled F, stable. Europium 2 plus, half filled F, stable. You got europium comes before gadolinium or near to gadolinium. So this will be 4f7, 5d0, 6s2. So 2 electron lost from this one. So europium, if you want the general one, europium you can write. Okay, it will be 4f7, 5d0. Sum of the D will be 0 and 6s2. So 2 electron if it is removing, 4f7. 4f7 means half filled. Okay, Then see, sub question C, why is actinoid contraction is greater? What is actinoid contraction definition? That you tell first. Actinoid contraction is same like lanthanoid. There is a gradual decrease from actinium to lawrencium. Actinoid starts from what? AC, ending as lawrencium, LR. Okay, so actinium to lawrencium, there is a gradual decrease in atomic size due to what? Poor shielding effect of 5f electron. Instead of 4f, you have to say 5f, because 4f is for lanthanide, 5f. That is called actinoid contraction. There is a gradual decrease in atomic size from actinium to lawrencium. That is the last element, lawrencium, due to poor shielding effect of 5f electron. But they are asking here why actinoid contraction is greater. Because 5f orbital has more poor shielding effect. Okay, or more poor shielding effect means their shielding effect is the least for which one? 5f, comparing with which one? 4f. So when you compare the shielding effect of 4f and 5f, 5 has the least shielding effect, okay, than 4, or lesser shielding effect than 4f. That is why the actinoid contraction is greater than element to element than this one. Okay. So hope you understood all these questions. So these questions you focus only these elements, you keep in mind. Europium, okay, cerium, and this one gadolinium you keep in mind. Cerium plus 4 you keep in mind, it will be 4f0. That is a stable state. Okay, and lutetium 3 plus 4f14. Then gadolinium 3 plus is 4f7. Half filled you write except lutetium, then you will get the mark. Okay, that only, otherwise no need to remember the number and all. This is the way you remember, you will get the mark. So this question was there in the previous board. Yes guys, almost all topics and all questions from the first 2 chapters under inorganic are over. Hope you got so much information and so much idea to solve or how to approach these type of questions. Okay. So shall we continue for more half an hour? So we will go for the biomolecule. Important topic only I'll be yes half is important topic we can discuss, and we will be finishing those chapter. Okay, so we can go. Yeah, Allah. Yes, Nadin. Okay, 1 second. Yes, now biomolecules. Yeah, this is the last chapter. Anyway, we can go for biomolecule chapter. So biomolecules, yeah, this is the very interesting topic for you guys, right? All you like biomolecules? Math students means yeah, anyway, it's a continuous 2.5 hour session means I know, but we don't have any other option. Most of the question, important question only we will touch and we will finish as early as possible. Okay, see, biomolecules, classification of carbohydrate. Based on this one, you may get a question what they are asking. Identify the polysaccharide. You know that one, carbohydrates are otherwise called saccharides. There are monosaccharides, disaccharide, trisaccharide, tetrasaccharide, and polysaccharide. So we have polysaccharides. So which all are polysaccharides? Polysaccharides, you know that one, starch is a polysaccharide, cellulose is a polysaccharide, glycogen is a polysaccharide. Cellulose has a formula C6H10O5N. Isn't it? N because of it's a polymer. Polymer means many molecule will be combining to form a molecule. Yes. Only starch, yes, well done. Only among this one, starch. You know the formula of maltose is what? C12H22O11. It's a disaccharide. Glucose and fructose has the same formula, C6H12O6. It's a monosaccharide. These two are monosaccharides. These two are monosaccharide. This is a disaccharide. And this is a polysaccharide. Keep in mind. Yes, Dhruvil, tell. Starch is a polysaccharide. Maltose and sucrose are disaccharide. Glucose and fructose are monosaccharides. Okay, fine. We will go to question number 2. So the next topic is structure of glucose. You know that one, glucose has a cyclic structure and that cyclic structure and the aldehyde functional group, everything, it has been proved based on few reaction. That is very important. Yes, that they asked in so many question paper. That is the question I kept over here. Write the product obtained when D-glucose reacts with NH2OH. D-glucose means can write the open chain formula like this one: CHO, CHOH 4 times, then CH2OH. Fine. This is the glucose we can write for reaction. This one reacts with, they are asking NH2OH, hydroxylamine. So I will write the H2 on left side, NH2OH. Then you know that one. Here the reaction takes place, and why we are using this reaction? What will be proved? Yes, very good. Allah. Oxime will be formed by reaction. So if a compound gives oxime when reacts with NH2OH, hydroxylamine, which means it consists of a carbonyl functional group. It can be either aldehyde or ketone, but a carbonyl functional group is there if it reacts with NH2 to form oxide. So here the reaction takes place like this one. H2 and O will be removing. Then you will get CH, okay, double bond N, single bond OH. That is called oxide. Then CHOH 4 times will remains as the same. This is CH2OH. This compound is called oxime. So we are getting oxime means it proves the presence of, yes, glucose, glucose oxime, correct. This reaction gives the proof of an aldehyde or carbonyl functional group in glucose. What is next? They are asking, this is answer for A, then answer for B. Sub question B. Write the structure of the product obtained when glucose is oxidized with nitric acid. You know that one, same. So CHO, then CHOH. Sometimes they may ask to write the equation also. That's why I'm writing CHO, CHOH 4 times, CH2OH. This glucose when reacts with what? Concentrated nitric acid and bromine water, we have a reaction. Yes, yes. Concentrated nitric acid when added to glucose, what will you get? You will get, yes, tell, saccharic acid. What is saccharic acid? Aldehyde functional group anyway, even with a mild oxidizing agent, it will convert it as COH. Okay, that has been converted. After that, this is the secondary alcohol that will not be converting. Here there is a primary alcohol. Primary alcohol in presence of strong oxidizing agent will be converted as what? Carboxylic acid. So we have 2 carboxylic acid. What is the name of this one? Yes, saccharic acid. So we are getting saccharic acid when glucose reacts with the concentrated HNO3. Instead of concentrated HNO3, if you are using bromine water, only on top COH will be there, the down will be CH2OH. The name of that compound is what? Gluconic acid. Gluconic acid. Yes, saccharic acid. Yes, saccharic acid will be formed. So you will be getting this one. After that, write the product formed when glucose reacts with the bromine water. That's what I said. So I will write the arrow over here. I'm not writing again this one. So you can write Br2, okay, /H2O. Bromine water means it's a mild oxidizing agent. Bromine water can convert only the CHO group as COH. So you will be getting COH on top. After that you will be getting CHOH 4 times. Then here it will be CH2OH. What is the name of this one? This is called gluconic acid. Okay, gluconic acid. Correct. So you will be getting gluconic acid. Yes, correct. What are anomers? It's a question. Important. What are anomers? Bio people means you might have a good idea. So what are anomers? Anomers means, you know that one, for glucose there is an structure called Haworth projection formula. So I will add a page over here and will write. So Haworth projection formula means glucose can be easily represented like this one. For understanding easily, because anomers they ask so many cases. Here you can put oxygen, because here it is. This is the cyclic form. Here carbon, second one, third one, fourth one, fifth one, and sixth one. So here you know that one. Here OH will be down and here it will be H. Here OH will be down and here it is H. Here it will be opposite, HOH. Here it will be OHH. Okay, here it will be H and here it will be CH2OH. This is the structure of glucose. This is called what? Alpha D glucose. What is that? Alpha D glucose. And how do you draw beta? No, they would ask for the structure. Nowadays the structure based questions are less. But this is for understanding what are anomers. So here we can draw again, here carbon, 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 carbon. Here it is carbon. Here OH will be on top, H will be down. Here it will be OH on down. Here it will be H. Here anyway, H is here and here it is OH. That's the structure. Here it is OH and H. Here it is H, here it is CH2OH. You know the name of this one, OH is on top means what? Beta D glucose. What is that? Beta D glucose. So what are anomers? Anomers are nothing but, okay, sugar which differ only by the, sugar means this one, carbohydrates only or saccharides. Sugar which differ only by the orientation of OH groups in C1. C1 means what? Carbon 1. This is the carbon 1. So at carbon 1, if the OH groups are oriented differently, how it is oriented differently? Here OH is on top, here is OH on down. That is called alpha, this is called beta. So what are anomers actually? Anomeric carbon. Yes, exactly. Here the anomeric carbon is which one? C1. So the definition is what? Sugars which differ, okay, sugars which differ only by the orientation of OH groups at C1. At C1 means at carbon 1. So at carbon 1, OH groups are oriented differently. Such a pair is called what? Anomers. Hope you understood. So that is the definition of anomers. Important. Alpha D glucose and beta D glucose is a pair. The pair only will come as anomers. Anomers is a type of isomer. Okay, sugar which differ only by the orientation of OH group at C1. That is called anomers. What do you understand by the term glycosidic linkage? Another important. Tell what is glycosidic linkage? Yes, at C1, Nitin, correct. Alpha or beta is, yes. Alpha will come, alpha means OH is down. Yeah, this is the alpha one and this is the beta one. Alpha D glucose and beta D glucose. Yes. Now we need to explain what is glycosidic linkage. See, glycosidic linkage I will explain with the same formula. We can go back and see, glycosidic linkage is nothing but, you know that one maltose, right? That is another question, so I can give that idea also. Maltose when hydrolyzed, what all components you will be getting? 2 alpha D glucose units, right? Maltose is a disaccharide, isn't it? Maltose is a disaccharide. How maltose is formed? Maltose is formed by combining 2 alpha D glucose. Here alpha D glucose is there. That's why I came back to this page. So here it is oxygen, here carbon, here carbon, here carbon, here carbon. I won't draw all these one. It will be wasting of time. You keep in mind here OH is down. That is because alpha D glucose. Here anyway H is there. Same type of another alpha D glucose I will draw. Okay, here oxygen, here carbon, here carbon, here carbon, here carbon, here carbon, and here one more carbon. Yes, see. Here you know that one. Okay, so here the C1 between this one. So here we are going to connect like this one. Here there will be an OH. So between these two OH, what is going to happen? This one, this OH and H will be removing. Okay, so this OH and H will remove. Then what will get? You will get an oxygen bond. So no need to draw. See, just for understanding, that's what I'm saying. No need to draw. Maltose has 2 alpha D glucose units. How they are joined? Alpha D glucose units are joined by removing water molecule between 2 sugars. Yes, carbon, oxygen, yes. Easily you can remember COC bond. What is COC bond? Here it is carbon, then oxygen. Because water has gone, one oxygen remains, again to carbon. The definition for glycosidic linkage is the oxide linkage formed between 2 sugar units by the elimination of water molecule. What is glycosidic linkage? The oxide linkage formed between 2 sugar molecule by the elimination of water molecule is called glycosidic linkage. Example, in maltose, 2 alpha D glucose units are linked by which one? By glycosidic linkage. So anomer I gave the example, glycosidic linkage, maltose has 2 units, alpha D glucose and beta alpha D glucose 2 units. That is linked by glycosidic linkage. So I think here the questions are over for this one. Yes. Now we will go to question number 3. Explain the term mutarotation. This mutarotation is also based on alpha D glucose and beta D glucose. What is alpha D glucose? A freshly prepared alpha D glucose. Okay. So if you have a freshly prepared alpha D glucose unit, it has a specific rotation. What do you mean by specific rotation? It rotates the plane polarized light towards right, and the value is 112 degree. but gradually it decreases to 52.7 degree. Which one? Alpha D glucose freshly prepared means the beginning you will get a specific rotation of 112 degree, gradually it decreases to 52.7. What about beta D glucose? Beta D glucose has a specific rotation of plus 19 degree. That will gradually increases to which one? 52.7 degree. Now there is a coinciding point or meeting point, which means alpha D glucose has a specific rotation of 112 degree, which will decreases to, okay, when you keep it as undisturbed, standing for few time, keep it undisturbed, its specific rotation will come down as 52.7. At the same time, beta D glucose, the specific rotation is 19 degree, it will increases to 52.7. Correct? That means this is called the term called mutarotation. Mutarotation means that specific rotation will attain an equilibrium value. This is called yes, it's a type of ether linkage. For the previous one you are asking, right? Allah Muhammad, correct? Carbon oxygen, it's a type of ether. So oxide linkage, yeah, that is the word we can use. Mutarotation, yes, mutarotation is the part of syllabus. Okay, mutarotation means alpha D glucose, it's there in the reader, you can read. Specific rotation 112 comes to 52.7, and for beta D glucose from 19 to 52.7 it increase. That is called mutarotation. Define the terms denaturation of protein. Next topic we are going to explain. We have few more topics. Yes, proteins. You know that one, protein is an important topic. So protein, they are asking what is denaturation of protein. Tell, you know that one, protein has four, based on the structure of protein can be categorized as primary structure, secondary structure, mutarotation. This much only you need to write. For freshly prepared, alpha D glucose has a specific rotation of this much, that will decreases to this value, and for this beta D glucose 19 to 52.7, this type of change in specific rotation for a pair of sugars is called mutarotation. Okay, change in the specific rotation to an equilibrium value for a pair of sugars is called, or isomers, isomeric compounds in which the specific rotation attains a equilibrium value, that is called mutarotation. What is denaturation of protein? You know that one, protein when subjected to undergo physical changes like change in temperature or chemical changes like change in pH, then the primary structure remains the same, whereas the secondary and the tertiary structure will be changing. Yes, and it loses its biological activity. That is called denaturation of protein. So what is denaturation? When proteins are subjected to undergo either physical changes like change in temperature or chemical changes like change in pH, their secondary and tertiary structure will be changing, or their tertiary and secondary structure will change, whereas primary structure remains the same. This is called denaturation. Due to denaturation, the biological activity will be disturbed. It losing the biological activity. Yes. What is essential amino acid? Essential amino acids are non-essential and essential are there. Essential amino acids are amino acids which cannot be synthesized in our body. Essential. Non-essential amino acids are amino acids which can be synthesized in our body. Glutamic acid, aspartic acid are the non-essential amino acid because they are already synthesized in our body. Non-essential. Glutamic acid, aspartic acid. So what are essential? Essential amino acids are amino acids which should be supplied through diet. So essential amino acids are amino acids which cannot be synthesized in our body. Okay, histidine, valine, all are example for essential amino acid that you have to keep in mind. Histidine and valine. Yes, amines, yeah. That next one, write the name of the linkage joining to amino acid. Amino acids are joined by, yes, peptide linkage. Okay, so amide linkage you can say. So the what is the linkage between the two amino acid? Amino acid means you know that one, it will be having carbon with the NH2 group as well as COH group. There will be H and R. You know that one. This is the one amino acid unit. The another amino acid unit you can write. Here it is COH. Okay, here it will be C, here it will be H, and here it will be R, and here it will be NH2. NH2 can be written as NHH. H will be removing from here. Here anyway, one H will be removing. Okay, so you can write NHH. So NHH. What happened? This H and this OH will be removing. CONH linkage. That is the amide linkage. Amide linkage formed. Yes, it's called peptide linkage. Yes, the amide linkage formed between two amino acid units by the elimination of water is called peptide linkage. Important. What is that? Peptide linkage. So what is a peptide linkage? The amide means why it is called amide. CONH group is coming. The amide linkage formed CONH group. Yeah, CONH group is CO and NH will be interacted. The amide linkage formed between two amino acid units by the elimination of water molecule is called that is called the peptide linkage. So that is also important. Question number 5. See, question number 5 is based on the alpha helix is a secondary structure of protein. You know that one? Structure of protein can be classified as primary, secondary, tertiary and quaternary. Primary represent the sequence of amino acid units which are used to make a protein. Amino acid, poly amino acids are called proteins, right? So sequence of amino acid means which all amino acid has to be joined to get a particular protein. That is called the primary structure. What about secondary? Secondary are of two types. What are the two types? Alpha helix and the next one is what? Beta pleated. So alpha helix and beta pleated are the two types of secondary structure. What is secondary structure represent? Secondary structure represent the winding and the twisting. How the polypeptide chains are twisted and winded to form a protein. That is called the secondary structure. In alpha helix means you know that one, it has a right-handed staircase like structure in which you know that one two amino acid units are combined like this one. Here if it is C double bond O, here if it is C double bond O is there, another one will have NH. So that NH and CO will be joining like this one. Okay, so this is the NH and CO, so NH. So one from polypeptide chain C double bond O will be interacting with what? NH. This is the hydrogen bonding. H and oxygen is interacting means that bond is called what? Hydrogen bonding. So what stabilizes the alpha helix structure? Alpha helix structure of protein is stabilized by hydrogen bonding. So hydrogen bond stabilizes the alpha helix structure. Beta pleated is nothing but instead of this right-handed coiled like structure or staircase like structure, it will be stretched out to a maximum extension. That's called beta pleated. Anyway, here the correct answer is what? As hydrogen bond. Polypeptide chain into right-handed screw like structure. Which type of interactions are responsible for the making the alpha helix structure stable? You have to write hydrogen bonding. Hydrogen bonding. Okay, so that is an important question. Electrostatic force, yeah, disulfide bonds, yeah. Hydrogen bonding, if you are writing for chemistry, that is fine. For chemistry, if you are writing that hydrogen bonding, you will get the mark. That is the only point they gave in the syllabus for chemistry. Give the difference between nucleoside and nucleotides. So now we have the topic nucleic acid. What are nucleic acid? Nucleic acids are polynucleotides. What is that? Polynucleotides. So polynucleotide means you know that one, nucleic acid. Nucleic acids consists of three different units. One is what? Ribose sugar, right? That is a 5 carbon pentose sugar we have. What in by pentose sugar? Pentose sugar means a 5 carbon containing sugar is there. Deoxyribose. Okay, that is why we have DNA and RNA. Then ribose sugar. So deoxyribose and ribose sugar we have. That is the pentose sugar. Next one is what? Nitrogen bases. Heterocyclic nitrogen bases. We have nitrogen bases. Then after that we have phosphate group. PO4. Okay, 3- group. We have phosphate group. All these when combined together, that is called a nucleic acid. So this nucleic acid consists of these three units. Pentose sugar is there, nitrogen bases are there. So nitrogen base we have two types. Purines is there and pyrimidines is there. Which all are purines? Purine is adenine and guanine. Okay, then pyrimidines, you know that one, cytosine, thymine and uracil. Okay, so phosphate group, these all. Then what they are asking, what are nucleoside? What is a nucleoside? Nucleoside means the first two. A pentose sugar when combines with a nitrogen base, that is called a nucleoside. What is a nucleoside? Nucleoside when combines with the phosphate group PO4 3-, that is called what? A nucleotide. Nucleotide. Hope you got the idea. So a nucleic acid means all these three units when combined together, that's called a nucleic acid. Pentose sugar, two types are there. Deoxyribose, that means that forms DNA. You know that one. Ribose sugar, that for RNA. Difference between DNA and RNA and all they can ask, it's a part of chemistry. So pentose sugar, this one, nitrogen bases, two types we have, purines and pyrimidines. So purines, adenine, guanine and pyrimidines, you know that one, that bases are different in DNA and RNA, we can discuss. Phosphate group, the first two, a pentose sugar when combines with a nitrogen base, that's called a nucleoside. That nucleoside plus phosphate group is called a nucleotide. Name the two classes of nitrogen containing bases found amongst nucleotides. That already I gave. What are the two classes of nitrogen containing bases? Yes, where you people are you there? Yes, respond. What are the two classes of nitrogen containing bases? Two classes of nitrogen containing bases are purines and pyrimidines. Okay, we have purines and pyrimidines. So purines and pyrimidines, yeah, yes, Allah, Muhammad, correct. Purines and pyrimidines, yeah. Purines means we have these two and pyrimidines we have these three. Yeah, that you keep in mind. Adenine and guanine, thymine, cytosine and uracil comes under pyrimidines. Yes, bio people will have more idea. Loyal men. Okay, fine. So next question is, yeah, I think the fifth one, vitamins. Vitamin is the syllabus part. Vitamins. Name the vitamin whose deficiency causes night blindness. Anyway, easy part. Tell. Now we can wind up. Before winding up, you tell. Very good. All are, send your answers. Hello. Get up, everyone, and send your answers. Yes. Vitamin K. Yeah. First one is what? Anyway, vitamin A. Okay. Night blindness. Then poor coagulation of blood is vitamin K. Yes. Yes, Devananda. Correct. Kevin. Good. Albert. Okay, so this is A and this is K. Okay. Yes, fine. Now I think, yeah, the last and final, we have the question. Yes, the very last question we can discuss. Almost all important topic we discuss. Vitamin, yeah. Now, yes, all are sending. Good. And thank you so much. Name the water-soluble vitamin, which is a powerful oxidant. See, we have two category of vitamin, that is fat-soluble. So, which all are fat-soluble vitamins? Which all are fat-soluble? A, D, E, and K. Okay, keep in mind. ADEC. You can remember easily. Then water soluble. Water soluble means remaining only, right? Water soluble is which one? B and C. B and C are water soluble. Yes. ADEC. Fat soluble means A, D, E and K. Water soluble is B and C. Here they are asking about water soluble. Water soluble vitamin, which is a antioxidant, powerful antioxidant. Which one is the powerful antioxidant? Yes, C. B and C are water soluble. Water soluble vitamin is B and C, which is a powerful antioxidant. Powerful antioxidant is C. Give its natural sources. Very easy. Yeah, tell. Natural source of vitamin C is citrus fruits. All yes, orange. Citrus fruits. Citrus fruits is a rich source of vitamin. Yes. Yes, so we finish almost all questions. Yes, guys, few more words we can wind up. Listen, see, for this inorganic chemistry, almost all category of questions we have discussed for this the chapter. Yes, practice all question. If there is any question, if you are not that much confident, practice it again. These are the possible question what we are expecting for your exam. And dear students, it's not about studying hard, okay? It's smart studying, okay? Keep a positive attitude towards your exam, perform well, and good luck. We are expecting result, a better result, best result this time. And thank you so much for watching. Thank you all, and all the very best. Good luck.
Brilliant Qatar, your trusted coaching partner for IIT, JEE, NEET, Science and Commerce tuitions with 10 years of excellence in quality training. Brilliant Qatar.